You can bring your coffee and tea along inside. So as we start, a very warm welcome to all of you here for this workshop on AI for sustainability, which me and Prof Weng are leading here. Today we will sort of talk about the broader perspective for AI for science and then deep dive into AI for sustainability. So to kickstart this session, I would like to invite Kedar, who will take us through this broader AI for science initiative that is started by NRF. Kedar.
Thank you. Good morning, everyone. Thank you for coming. Really appreciate it. I'll only take about 5 minutes just to get you the broader context, as Madhavi mentioned, about what we're doing here. The initiative kind of started in January or maybe December, and the idea is to actually explore what AI for science means in Singapore. So it's actually bringing the community together, having discussions in each different domain. Right? And a complementary effort that's been ongoing for a few years is led by Professor Hiroki Kitano. Advance the slide. And his idea of doing AI for science is a little bit different, but the idea is very interesting, right? So can you actually have a Turing test and Nobel quality scientific activity? It means that you have an AI system that gets the Nobel Prize without noticing that it's an AI system, not a human scientist. Right? Maybe it takes a few years to get there, but we are thinking along the same lines. We are actually looking for AI for science, and we spent some time doing the foundational study, the capability study, and you can find this online on the aiforscience.sg website. I will flash the link in a few minutes, right? But essentially, the idea for AI for science here is to use AI to solve scientific problems for discovery. Okay, so it's not really the science of AI, which is development in AI itself. Like you can go to all these top AI conferences, and there's work being done in different kinds of architectures, GANs, BAE, so on and so forth. We call that foundational AI. There's a lot of people here in Singapore doing that, which you can leverage for your domain. And there's also AI for X, right? And perhaps sustainability actually sees a lot of this already, where you take existing tools, optimization, etc., and you can apply them in particular sectors. So we're not looking for this either. What we're looking for is how can AI transform the field of sustainability, where the grand challenges are informed from the field of sustainability with all the subdomains that you've nicely identified, and then we're actually using AI to hit those transformative goals. And the way it's been done is actually a little bit of top and bottom. There's domains, of course, that are of national interest to Singapore, right? And those have also been crafted as workshops. And there's also bottom-up ideas that have come up, like digital phenotyping is one of them, complexity and physics is another one that came from the bottom. And the additional considerations are really critical, like data and computational resources. So we're actually engaging with, let's say, NSCC to have discussions for what kind of data will be needed. Does the data already exist? So please have this as a part of your discussion today when you discuss during your breakout sessions, and do make it as quantitative as possible in order for us to frame this properly, right? So this is the timeline. We're currently here in the thematic workshops. It's actually tagged on for about a month or so because of so much interest from the community. We've had study trips. NRF has actually done some study trips both to Europe and the US, and we're collecting information from what AI for science means over there. Myself and Dr Zhiquan Yeo in NUS Computing, we're drafting the foundational study report. So this is where we'll ask Madhavi's help to actually have a 3 to 5 page white paper stemming from the discussion that you've had today, right? So please, I will describe what we're looking for in a few slides, but that will be a part of the foundation research capability report. And this is a public-facing report, right? So we'll actually send it out to all academics, government agencies, and also internationally. So it should be done by probably July or August this year. And please mark these dates, 23rd and 24th July. It's going to be an AI for Science and Nobel Turing Challenge Initiative conference. We're inviting luminaries from around the globe to come. We currently have participation from MSR. We're exploring with DeepMind, IBM Research, NVIDIA, apart from other top academics as well. So it's going to be quite a fun couple of days. And eventually, NRF is looking to launch a grand challenge proposal. So this is basically the end point of this, is to have a national initiative on the AI for science, which across the board here is leading that effort from NRF. So we've had many workshops. This is actually a living website, AI for Science.sg. My team in the back there is actually helping me do this quite a bit. AI for Science.sg. Please follow it. This workshop will also have a summary and photos from today will be taken and uploaded over there. So please engage with us. So what are the outcomes that we require, right? So these are the questions that actually we'd like you to answer. Vision statements. Please be bold, right? Please have problem statements and targets for AI for science and sustainability. What does it mean? What is the grand challenge that you can solve that is not possible today, right? And what we're looking for is in the context of AI for science, How is Singapore well placed to solve this? What are the challenges and bottlenecks? And the data, very central. We don't mean that you already have the data. It could be a data collection exercise in the first year or so. And how is Singapore uniquely placed for this, right? So please remember this, transformative data sets and HPC resources, GPUs or CPUs needed, right? And my last slide is sort of an illustration of what this looks for, right? So people ask me about the TRL levels. It's a nice slide to clarify things. Foundational research is basically building peaks of basic AI excellence. Applied research is using AI to drive use cases in priority sectors. And AI for science sits nicely in between, right? And in material science, I'm a material scientist by training, we actually develop the AI algorithms more in order to solve material science problems. One example of this is, for instance, symmetry constraints that are put into design of materials crystals, right? And you have to actually change the way the architecture of the machine learning is done to solve that problem in generative design. So here's an example, right? You actually have material science here. Foundation models are actually foundational AI research, like VAEs. And then you can have property-directed generative design of materials. That's actually AI for science. And then you can use this that you have developed to actually have, let's say, new catalysts or hydrogen evolution reaction materials, etc. So what we would really like is to have this sort of picture that's painted and show us where AI for science sustainability stands. Right. So that's what we're hoping out of the workshop today. Thank you very much again for taking your time and prospect. Any questions about this? Yeah, a quick question or two.
Yeah, any quick questions for Kedar before we move on? Maybe as they go along, they might have some questions. So in the next section, I'll give a very, very brief introduction of why these themes, the motivation for AI sustainability and these themes, and Lee Wang will come and pitch in on the challenges. So when we were discussing this workshop with Kedar on AI for sustainability, as you all very well know, sustainability is a very broad topic. So what we did in coming up with the themes for sustainability is we sort of looked at the past workshops as I've listed down here. There have been several workshops that focus on climate science, complexity, material science that happened before. And during these workshops, many of these touched a lot on sustainability related topics. So what we thought we would do is we thought we would narrow down the sustainability towards our decarb journey, our decarbonization journey, specifically on reducing the scope 1, scope 2, scope 3. I've just shown the illustration there. Scope 1 is the direct emission, scope 2 is the indirect emission, and scope 3 is the value chain emission. So we sort of thought, and when we looked at the other workshops, these were not covered too much into detail. So these workshop themes resonate with this decarb journey towards scope 1, scope 2, scope 3 reduction. And we also had the backdrop and the background of our national priorities, Singapore's national priorities of how do we fast forward our national targets and goals. All of you are aware of the Singapore Green Plan 2030. In that, we will heavily look at the pillar of energy reset. The other pillars have been covered in the other workshops. And also in the energy reset, there is a low carbon kind of a roadmap and a trajectory that Singapore government has come up with. So with these as backdrop, we have narrowed down to 4 themes that all of you would help us to deep dive today. And those 4 themes are listed in the next slide. So these are the 4 themes. First is future grid. Next would be carbon management, electrification, and the last is urban nexus. The topics are very broad because we want to give you a leeway to discuss. You're all the subject matter expert. We wanted to give you a leeway to discuss on these topics. And I have sort of shown some dots right next to each of the topic to show that each topic covers scope 1, 2, 3 at different extents. Some of them cover scope 3 more, some of them cover scope 2 more. So this is sort of the background and setting the scene for today's discussion on the 4 topics. And later, after my presentation, you'll hear from the subject matter expert on each of these topics in a minute. Moving on, I thought before I pass my time to Lee Wang to talk about the challenges, I thought I'll just go through I'll go through some of the, I didn't cover this. So, Kedar spoke about top-down and bottom-up. So for this particular workshop, the top-down areas are really the four themes that I spoke about. The bottom-up, where we need your help in discussion, is, hey, what are all the bottom-up enablers where AI can come in and play a bigger role, a critical role in these top-down themes? I've just given some examples of what role AI can play: digitalization, data harmonization, adoption of AI in this, and also human in loop. And these are just some pointers which later Wan will deep dive into this, but there might be more. And that's what we are asking your help to flush it out today during your deep dive discussion. Is it working? I can take that. So I thought I'll just set the scene for four topics very briefly without taking too much time. So this is really the broad stroke picture of what are we looking at in future grid. We are really looking at, can we orchestrate the future grid of tomorrow when we have various distributed energy resources. Singapore is talking about importing 4 gigawatts of renewables from overseas. Where does storage play a role? And how is the future grid going to look like? And how can AI enable or accelerate this entire transition, energy transition pathway, is what we will be discussing about in the workshop. The next theme is carbon management. All of us are aware of this topic, but what kind of new innovations, processes, mechanisms that we need to facilitate carbon management? And here we are not only talking about new technologies, for example, like in carbon capture, but in each process, can we look at the software aspect of it, the whole of life carbon analysis? How can we ensure that in any process we are talking about, there is a whole of life carbon analysis and also towards a low carbon energy transition? We are also talking about the other side of carbon management, which is reporting. How do we collate the data in terms of carbon? How do we report? How does ESG reporting play a role in new technologies, in existing technologies, in industries? Later, you'll have a speaker talking a bit more, Vish will talk a bit more about this carbon management. But these are the broad questions we are asking. And of course, the goal always is, can we close the loop when we talk about carbon management? The third area is electrification. All of us are sort of aware of this. Singapore has a target of EVs, all EVs on road by 2040. And from 2030 onwards, there are no new ICE engine purchase will be allowed in Singapore is the target. And if that as the backdrop, how do we really go towards this journey, and how can AI help us in this journey of displacing fossil fuels and going towards electrification, both at the component and system level? So I've thrown out some questions which can be a part of your discussion. Can we really empower innovations in electrification? Can we really reimagine our operations? There's not going to be petrol stations anymore. Do we envision all our charging stations? Where are we? And more critically, how can AI enable this transition of electrification? That would be the topic of discussion. The last topic is really urban nexus. It looks a bit broad, but we thought it is very interesting and important to talk about it in the sustainability, is because every time when people talk about energy, water, food waste, many of the times they are spoken about in silos. But this particular topic we thought is really an intersection of multi-vector, because if you are trying to do urban farming for food, but you eventually increase the amount of energy and carbon, that is not a very sustainable solution. So how does all of these different areas, energy, water, waste, food, etc., interplay in a way that overall, in a system level, at a broad level, we decarbonize and go towards a sustainability journey? So that is what is this area where we call it as a multi-dimensional puzzle or a multi-vector problem that needs to be considered overall for AI for sustainability. And AI can definitely play a very critical role in this because of its capability, its breadth and depth, that it can look at multiple dimensional problems. And that's sort of what's the discussion in this particular topic. So with just setting this theme of AI for sustainability and the four themes, I'll pass the time to Prof Weng, who will sort of deep dive into the challenges. What are the real challenges in these themes and in sustainability?
Morning. Good morning, Kedar and Madhavi. Just give you all the ideas. As a chief sustainability officer, I don't know what to do with this. That's why I'm going to ask you all the questions and give you all the challenges and see whether you can help me with them or not. You are all the scientists that can work on innovative solutions. So first thing is data quality and availability. I think this is always critical for success of AI, and I believe that most of you already know. And therefore, I think it's important for us to look for that. And not all data is always available. And for example, right now, we don't even have a standardized emission factor, localized emission factor database in Singapore. So we rely on overseas foreign IPCC, which will actually have certain bias. So that is the issue with not having availability of data. The other aspect is as we continue to integrate AI into our work, then we find that there will be a lead to increased e-waste. And this is due to increased demand for lots of CPU, GPUs, and also memory chips. And it has been predicted that globally, you expect e-waste to go up to 70 megatons by 2030, and out of which 70% will actually go to landfill and toxic waste. Singapore alone, we are already 60 kilotons of e-waste a year, and it's growing 5 times faster than we do our recycling. So this is something that we want to make sure that while we look at AI, there is this issue on it also affects sustainability. Transparency and ethics. In order to, in fact, most of AI developers, in order to make sure that they have competitive advantage, they always operate AI as a black box. So actually, this actually makes it very difficult for us to understand the model, especially in decision making. And actually, for some algorithms, because they rely on past historical data, it inevitably perpetuate bias that can then lead with not reasonable or valid decision. Therefore, we want to make sure AI transparency and fairness to avoid unnecessary discrimination. Another common challenge is adaptability. AI solution, while it may work well in a controlled test environment, may struggle to scale and adapt to the dynamic real-world situation condition. And then, in order to build a robust and adaptable AI system, for this can be a challenge. And therefore, also even if you have an AI model, how are you going to incorporate human behavior and compliance? That remains still a difficult issue. I share with you later that some aspect of human behavior that has been incorporated. And we always we need to examine long term. Sustainability, is an issue that it covers, is multidisciplinary by nature. So as technology evolves, we also need to make sure that regulation also look after ethics. Okay, yeah. So we also want to make sure that regulation needs to be put in place to address things like ethics, privacy, and security. Therefore, we need always to strike a balance between innovation and regulation. But the most obvious challenge is amount of resources that AI consumes. This is especially the case when you look at more complex model, which require lots of power to compute, simulate, and also to look at how we can work on complex problems. So in fact, just in 2022 alone, data centers consumed 5.2 billion liters of water. And also the demand for lithium has actually gone up and estimated to go to 1.1 megaton by 2040. So those are some of the issues that we want to take care the energy consumption is one of the key concerns. So I always ask myself, how accurate, how good is good enough? So you see that the energy just required to categorize iris flower up to 96% accuracy is 960 joules. But just to stretch for another 2%, you require 200% increase in energy. And for an additional 0.08%, more than 400% increase in energy. So this is the kind of energy consumption that you're looking at. When you stretch, when you level up, you get more and more energy demand. So we need to always ask ourselves, how accurate is good enough? So that's why we need people like you, scientists, to help us to work on all this, to address, to make sure that sustainably, AI remains sustainably in sustainability. I want to share one encounter I had with ChatGPT and Copilot. I asked a hypothetical question. I said, if my girlfriend said, if I say 1 + 1 = 2, and my girlfriend insisted that 1 + 1 = 3, what should I do? ChatGPT give me all list of long explanation to please explain to your girlfriend why 1 + 1 must equal to 2. Then ChatGPT. Copilot give me a long answer, but the short answer of it, Copilot said, if your girlfriend insisted 1 + 1 = 2, please agree with her. So the behavior part is there. So ChatGPT, Copilot AI has EQ. That's what I want to share with you. Thank you.
Thanks, Vivian. So we move on to the next session where we have subject matter experts talking about each of these areas. For each of these teams, we have 2 speakers. So I would like to invite the first speaker. So the first team is Future Grid. First speaker would be Prof Ren, who has come all the way from France to give us a talk. Thanks, Prof Ren. He's the General Director for G2E Lab, Professor at the University of Grenoble, Alps, CNRS, and he has another 1 page of affiliations, which I think I'll take up all your time if I take this, Prof Ren. Over to you. He'll be talking about emergent grid applications with need for AI and challenges ahead. Please put your hands together to welcome him.
Thank you, Prof Madhavi. Yeah, thank you. It's always a pleasure to be here, although I just arrived and still under the jet lag, so please forgive me if I'm a little busy, but I'm under the jet lag. And just the pleasure of sharing with you some of those thoughts regarding actually the alignment of sustainability, energy transition, grid of the future, and then AI. So that's my talk actually here. And I use for the limited time just to share with you some of those issues. And let me start with this, some of the facts of regarding, of course, this sustainability energy transition. The last years, since 2015, they were the warmest years ever recorded. And every month we say that this month has been the warmest month ever recorded, so having in mind that the coldest year that we know is 1909. And since actually since 2015, we have seen a number of objectives and laws on energy transition since the Paris Agreement. And then in Europe, we have all those new deal people 55 and so on, which most of them translated into decisions such as, for example, massive investment in renewable energies. Let me give you some of those figures. We are about between the last 3 years actually, between 450 to 600 billion US dollars invested every year in renewable energies. And last year, 2023, was a record high with the addition of more than 50% actually of renewable energy just for 1 year. We see that the movement is accelerating. And the same thing actually on the usages, for example, with electrification, Prof Madhavi has just talked about. With EV, last year it has been about plus 52%, and that also is accelerating. And the other number that is very interesting is also to the bottom of all this sustainability and renewable energy is that we had more than 300 million people gain access to First time I remember a few years ago, which means that less than 5 years ago, we are talking about 2 billion people without access to electricity, and now drop it to about 600 million, which is actually a fantastic achievement thanks to this development of those renewable energy. And these last years, we have seen some of the crises, starting from the COVID crisis that had impact actually on the energy consumption, but also on the emission, global emissions, but it was cyclic, which means that there is a reduction and then it takes off again, and this was cyclic. And then we have seen last year, particularly in Europe, that there was a huge impact actually on prices and spikes in the prices of electricity that have impact on the economy, on a lot of companies went out of business, etc. It's a huge effort, and still we are there. And now, when you translate that, all those renewable energies, for example, in terms of the grid, you know all that grid, so we go quite fast. It's the grid, we have different parts of the grid, but part of it is really, we had socially speaking, where we get electricity from the central point, goes from transmission all down to the end user distribution grid, and that's what we call it one way. But now we have this distributed form, that is a distributed energy, and those renewable in part of the grid. For example, in Europe, 95% of all renewable energies that we have in the grid, they are connected at the distribution grid, where that grid, historically speaking, was not designed for that purpose. And as a matter of fact, it has to be changed totally. And this is a big challenge because we have this bi-directional things where not designed in the grid. The arrows are not good, but we have considerable impacts. We have considerable impacts in terms of the operation, in terms of the planning, in terms of the fact that we are not users to have this kind of renewable energy in the grid that gave us challenges. For example, the variability that I will show you just after that. And the other thing is also the asset management. Asset management is one thing that is extremely important for AI. I will be back for that because I want just to stress where are the problems for sustainability. And the asset management, we have, for example, our grid is aging. The average age is about 30 years, which is okay, but we have some assets that have 60, 70 years old. And we have a risk of failures. And the risk of failures, every failure, 1 day of blackouts in France is about 1% of GDP, which means that it's billions of billions. We cannot afford that. In addition to that, the acceptability of the people. People, they don't accept anymore to get the power, because the power, when we switch off when we switch on the light, we want to get the light. We don't understand where it comes from, we want to get the light. And that's when the population becomes a granted service, or it's a basic service. Let me show you this couple of issues of this system integration. You can see, I don't know if you have this, you can see here, this is typically 10 megawatt of wind plant. Recorded over a year with 10 minutes something. And you can see the variability here, and we can lose actually in a couple of minutes, we can lose the whole power output that we can get from the district. And we have actually a constant in the grid that it should be balanced somewhere. It should be balanced. Someone has to take the balance, and that's a problem. And then we can go to the solar. This is the same solar. It's a power plant, solar power plant, 4 megawatt. Actually, it's in France, which is a good point, where we have enough solar, and the same thing. You can see the variability, and particularly when we have just a cloud that is crossing, and then we have that variability. And then we have here also the EVs. The EVs we have made in the experiment actually with the real people, saying that we provide them with the good signals, incentive signals, where they charge only when there is a value here. This is the curve of the consumption, and we'd like them to charge here. But as a matter of fact, because of the sociology of the people, because of the behavior of the people, they come, and when they charge only here. They charge here because whether when they are at work or when they come at home, and they charge directly, and we added the constant actually to this rather than actually we can manage that. So we have difficult issue of global issue, means that how can we master actually the generation consumption overall models, but also we have some working concern. The other thing is that most of the renewable energies, including actually also charging station for electrification, They are made of power electronics. Some of the people who are working in engineering know that. And that power electronics, the impact is that they reduce the inertia of the system. This is not good for us. Why it's not good for us? Because any disturbance that comes from the grid, then it will have a very fast reaction that grid is not used to that. And just to give you an example here, what we have, this curve is the response of the disturbance in the grid, frequency response. The black one is we don't have any photovoltaic. So it's just a dip here, and then it recovers. Then we have 20% with the red line, 20%. But we see that it's deep again. Okay, it's deep and it's recovered a little bit. Then with the 30% of the share, then we are here in the escalation phase because of that lowering of the inertia. And this is what's killing us, and that's why in some of the islands in Europe, it's forbidden to go beyond 30% of renewable energy, for example. That's the reason why we have these issues. I finished this this part with the need for adapting the grid quickly, and what are actually the issues where we need AI. First of all, we are facing now the ever-increasing complexity. Complexity for us is cost and vulnerability, and then we'll come back later about the resiliency. We need to fulfill changing costs and changing needs in terms of course, the new usages, in terms of the infrastructure independence, but also on the freedom, because instead of just saying the people, no, you cannot do that, you cannot do that, or how to organize the freedom. We have challenges linking particularly on how to renew the infrastructure and adapt this infrastructure in order to integrate a large amount of renewable energy sources and the new usages like electric vehicles and electrification through this application. Let me give you one example. We have spent more than 150 years to go from 0 to 25% of electricity in finite using energy. 150 years. We have to spend, we have to go to 60% of use of electricity in our finite energy within less than 25 years. This is a revolution. This is a revolution in terms of electrification, with huge challenges in terms of mastering what's going on, but also in terms of investment. We have the investment that we need to multiply from now to 2050 by 3, which we are talking just in France, we are talking about 200 billion euros. It's huge. We call it water investment. And the challenge is actually the big challenge is the resiliency. The resiliency, how we can make sure with this revolution somehow that we keep our system resilient with respect to the balancing of generation consumption in an uncertain condition. We are seeing more uncertainty than ever. And then we have to deal with this issue of this, having in mind this, of course, this resiliency, this variability or renewable energy and the inertia, the decreasing inertia. It's a threat for us. The digital with cybersecurity in terms of resiliency, and finally the climate change, because the climate change also is giving additional concern in terms of reliability. The global warming pushes some concern in our equipment, and that equipment we need to push preventive mechanisms, and that's why AI also will see that it is very important. And of course, we need to move to what we call flexibility, state of flexibility, and for that, we don't master yet what we call the dynamics and how to put more intelligence in order to master this flexibility. Now, with the opportunity and benefits of AI, actually, AI is not new in our field. We started working in AI in the 80s. In the 80s, but it was mostly academic work, mostly academic. And we have a number of issues like real-time flexibility, the voltage collapse, expert system to manage some disturbances, alarm processing, etc. So we did that work in the 80s, where we were talking about neural networks and so on and so on. However, at that time, we were facing for some limitations. And the limitation we talked this morning about the data availability. We don't have enough data at that time to take advantage of all the opportunities because of the AI. The second thing is that at that time, I did my PhD with industry, and the 80th, the first subject is actually pattern recognition for security things. And the industry said, well, we don't have trust in AI. We don't have trust because we cannot give AI, give us what we do. We are the operators, we know exactly what we're going to do, and there was no industry trust. And finally, of course, there are limits of AI techniques by themselves. We don't have, it's not the same as we have today. So what are the changes? What's new actually that we are all here? You are all here. What's new? The fact is that we are, as I just showed, we are facing this new paradigm linked to these renewable energies and new usage integration challenges that I showed. And particularly what we call the 3D energy transition, decarbonization, decentralization, digitalization. These are the three challenges that change the case. We are facing an increasing complexity and uncertainty. And we have already the target that is the most complex infrastructure ever built by humanity, and we have to increase that complexity for a certain stage. The widespread, of course, of digitalization, the data availability for several applications, because we now, for the first time, we start to have more and more data available because we get the data from smart metering, for example, with the customers, with the end user data that we have it, and we have, of course, some issues, obviously, but we can get that data almost on huge number of huge quantity of those data, but also increased sensors. I give you just one example. At the distribution grid, we have, no, at the transmission grid, we have 200% sensors embedded in the grid. It means that we have more data at the transmission grid than what we need because we need to recover the state of the vulnerability. However, at the distribution grid, we have 0.5% data. We don't have measurements. And now, because of all what's going on, we need to have more measurements. We need to see what's going on there, and then we are responding more and more sensors, and we get more and more data again. So that the data is still it's getting there. And finally, of course, is now the industry need. For the first time, we see industry need. I had examples where we have that industry applications in the power grid, of course, of the AI. And now, for the first time, I see industry coming saying, I need AI for my applications. And I trust AI to be used actually, which is a total change from the industry. And I know, of course, it's must have today with ChatGPT and what we said, of course, on Copilot, etc. It's must have today. We're all talking about AI. Now, what are the major AI today? Not because we are using AI because it's must have. We are using AI because they are bringing in added value that we are not able actually to solve the problem by traditional things. If we have our models, our techniques to solve those issues without AI, we will do it without AI. But we have the need for AI because we have some challenges to come only by relying on AI. We have some, I grouped it on some applications that I hope that we will discuss further. The issue of diagnosis, detection, observability, for example, on fault management, because the system is getting complex, we need the reactivity, we need real time, and that's where we need some AI as well. Forecasting, we see the variability of the renewable energy sources, but also the variability of the people. We have also a high variability at the usages like EVs and also the end user, and we need to have the short-term evolution of consumption and we will just short time. Today, the best accuracy that we get, is about 15%. That's it. So we need that AI and increase the number of data in order to improve our forecasting. And the market, Shriyang will say some about the market. Resiliency is number one. It has been voiced by all utilities worldwide, saying that the number one challenge that we are facing in the future, particularly with this intensification of electricity sustainability, is the resiliency. That's the number one issue. And we need to have models for assessing the resiliency, a solution in the context of high uncertainty. This is knowledge, high uncertainty. And as I told you, the impact of climate change, because we are making some prospect that with the global warming, for example, we have an impact not only on the equipment themselves, but also on an issue related to that if we don't have, give an example, we rely in Europe, not in France, we rely 80% on nuclear. Now we are getting to 50% on nuclear. Nuclear needs cooling. If we have that global warming without the water because of some reason we will have a drought or whatever, then we are in a bad situation. So that issue is very important to assess for the future. Design and decision making. We have the microgrid, we have the energy management, and so on. And the AI tools actually. Of course, we have different issues where we need classification, we need discrimination, but also we need decision making, fast decision making, for example, with the operator. And we come up with one thing that is important. Some of you are computer science, most of the processes say, okay, with the data, give us the data, we solve everything. And that's it. And then the people from the physics and from the grid, they say, well, we have our physical model and we have deterministic models and we can solve them. And actually, we know that data by itself is not enough, physics by itself is not enough. We need to couple the both models. We need to couple the physical models with the data. And that's where we are working. This is the solution. And that's really where we have, and this I finish with my slide here to show you exactly where is the AI for our application in the future. So we have in one side the problem to solve. I have described a number of those problems and a number of those challenges in one slide here. And then we have the AI techniques. We have the number of AI techniques where we all know those AI techniques in supervised learning, unsupervised techniques, reinforcement learning, whatever. And then you have all those techniques. But what makes the choice that they will choose this instead of this or that problem for that technique? And then we have another issue, which are the operational competencies that came from do we have access to data? Do we have the right data? You talked about that. Sometimes actually we don't have enough data that we need to have this observability. We need to find tools that provide us a model without necessarily accessing the enough data. And this is also not only because we have a large number of data, but not enough data as well. User involvement, the behavior, this is the interaction with the human. These are all operational items. And when you make the intersection actually, you have here in the middle what we call the relevant study and the case application. That in the discussion later on we should focus on. But as a summary, actually, that's what the messages that they would like to share with you is that clearly, in order to tackle those issues with sustainability, physics, etc., we need to couple the physical and the AI models. That's the hybrid model. That's one message. The second thing is that we know that all those machine learning models that I mentioned here, most of them actually, all of them, they need actually a large amount of data and quality data. So we need also to find the models that we can learn that solve our problem without necessarily accessing to a large number of data we don't have in some areas. And finally, actually, we think that the most relevant and efficient solution for grid operational tasks that we are doing is that it's a combination of AI techniques in order to tackle those issues that we have. That's I finished my speech here. Of course, I have some industrial use case example that Shuyan actually will focus on some specific application. And I'm here, I don't know if you have some specific question on my speech, but I'd be glad to answer the other.
Yeah, thanks for Praveen. Please put your I'm sure there are lots of questions for Praveen, but we have a very packed schedule, so we would request to have your questions and comment later during the discussion or break or during lunch break. Thank you for Praveen. So I would like to invite the next speaker on the future grid, Prof Yan Xu. Yan is a professor at NTU. He's also the director of the COP Lab with Singapore Power Group. So I'll pass the mic to Yan. Please put your hands to welcome Prof Yan.
Thank you, Professor Madhavi. Good morning, everybody. My name is Yan from NTU. My topic today is on the energy transaction mechanisms by AI. While Professor Nordin has given a very wonderful presentation on how AI is promising for future grids, today I'm going to give you a very specific work that makes use of AI to make profit in the electricity market. I will start by giving you a very general overview of the electricity markets, taking Singapore as the example. Generally speaking, the electricity market can be divided into wholesale market and the retail market. While in the wholesale market, the suppliers, which are power generation companies, will have to bid in order to sell the electricity in the market. So they will submit their bidding to the energy market operator, in Singapore case, which is energy market company, EMC for short. And after receiving the biddings from the power generation companies, the EMC will clear the electricity market and determine the electricity price. While the retailers will buy the electricity from the markets to sell to the consumers. And certainly the power will transmit from the generators through the grid to the end users. While for the consumers, they can also be classified into contestable customers and the non-contestable customers. For the former, that means if the customer has sufficient large capacity, it can register a market participant, which means the consumers can also participate into the electricity markets so that it can benefit from offering and bidding. Well, in the retail market, our local electricity market has been opened up since 20 years ago. So nowadays we have the so-called open electricity market, OEM for short. So this OEM allows more participation from the consumers as well as other market participants, so that opportunities can come for the contestable consumers to participate in the whole electricity market, so that it can make profits or have less electricity bills. So today I'm going to talk about a very specific work that we have completed 2 years ago for the microgrids to participate into the electricity market, so as to bid in order to have revenue or less operation cost. So basically speaking, the microgrid is a low voltage distribution grid with distributed energy resources integrated. While the distributed energy resources can include distributed generation, such as the solar PV panels, energy storage system, as well as the flexible customers that can flexibly adjust its power demand. So these microgrids can certainly be registered as contestable consumers. So in reality, this microgrid could be industry park or even could be campus. For example, our NGO campus can also be operated as a microgrid needed. So our objective here is to support this microgrid to participate into the electricity market, so that we can meet our energy demand or our energy production in order to make profit. So here we have designed a two-stage decision making. While in the first stage, we submit our bidding, including our demand and our production, because we have our distributed generation, we have our flexible load. So as the aggregated consumer, we can flexibly adjust our production and demand. While in the second stage, after we submit this bidding, we have to commit this bidding for the every 30 minutes. But certainly because we have stochastic solar power output and also our uncertain load demand, so we have to maintain the total power bidding in every 30 minutes. So you can imagine how complex the problem is, because the electricity price is stochastic, the solar power PV is also stochastic, and not to mention our load demand. So the whole problem is a very complex decision-making problem. So in this research, we aim to make use of reinforcement learning to solve this problem. Talking about the methodology, the reinforcement learning is one category of the machine learning. So unlike the supervised learning and unsupervised learning, the reinforcement learning does not require a training data set. So in this case, we do not face the issue of data availability. But instead, the reinforcement learning is to train so-called agents, which is a decision maker in this context, through iterative interaction with the environment. Which means every time the agent will make an action, then this action will change the status of the environment. And then the environment will return a reward to the agent. So the agent wants to continuously receive higher and higher reward, so that it can reinforce itself to make decisions in the complex environment. That's why it's called reinforcement learning. So if we apply this approach to our microgrid bidding problem, the agent will be the bidding optimizer, while the environment will be our power grid as well as the electricity market, and the state will be the power billings, total billings, electricity prices of the full market, and the action will be our bidding dividends of the microgrid. And the reward will be the total expected revenue that can make by our microgrid. And the action value will be the expected total reward over a time horizon. Well, the key research problem here is how do we model this microgrid bidding problem into this reinforcement learning, and in the meantime, how can we solve this reinforcement learning based on the existing learning algorithm as well as the power system physics knowledge. As Professor Nadine mentioned, sometimes we do not need a fully data-driven approach because power system have already the very good physics models. So it's going to be a hybrid model approach. Well, looking into the specific machine learning algorithm, basically the reinforcement learning can be divided into so-called value-based approach, such as the Q learning. Basically, the principle is to train a Q table that can match the stage and the division with a reward. But this Q learning is a very basic one. It has to discretize our dividends into discrete values. But clearly, the bidding problem is a continuous value-based problem. So we have to rely on the latest, so-called more advanced reinforcement learning approach, which is called policy-based approach. Basically speaking, the policy-based approach is to directly train a decision maker and to optimize the decision-making policy. So in this research, we adopt this policy-based approach. Well, under this policy-based framework, we design such a actor-created decision-making approach. So basically, the actor is to make decisions for the microgrid to be in the electricity market. And a critical network is to evaluate the performance of the actor so that it can support the training of the actor neural network. So in this structure, both actor and the critical network can integrate interactively so as to optimize the decision-making policy, which is to maximize the revenue that the microgrid can make in the electricity market. Next, I would like to quickly show some of the technical results. We consider a simple microgrid with 6 distributed generation resources, including solar PV, energy storage system, as well as the flexible load. We train this model in the Singapore electricity market with the historical data. And we also compare our approach with existing methodologies such as the stochastic optimization, robust optimization. So clearly, in this table, you can see that. So here we take the total operation cost as the objective, which is the operation cost of the microgrid minus the revenue net in the electricity market. So clearly, you can see that our approach can achieve a much smaller operation cost with the real-time computational capability, while the existing model-based approach takes more than let's say 200 or even 4,000 seconds to solve the full problem. But our approach can give a decision within just 1.6 seconds. And it also takes our approach in a larger bill testing system. And you can see here, this is our energy bidding in the electricity market. And this is the real-time power adjustment in every 30 minutes bidding cycle. While this research have already been completed, we also want to acknowledge the research funding from NRF through the AGE research program. However, looking forward, the approach is not perfect yet. There are a lot of work to do, especially leveraging more advanced AI for future grid. So basically, our opinions, number one, we need to look at the power engineering problem that really needs the AI. Like Professor Nadine mentioned, sometimes the model-based approach is not perfect. However, the purely AI approach is also not suitable. So it has to be a kind of hybridization of both physics-based approach and the AI-based approach. And the learning framework, it has to be problem-specific in fact. There is not a universal framework that can cover all of the power system problems. And also the physics informed learning, as briefly mentioned, we also make use of the physics knowledge of our power grid during the machine learning process. And the constraint satisfaction, certainly our power grid has a lot of operational constraints. During the machine learning, we have to satisfy these constraints. So how to satisfy these constraints is a very challenging problem from the algorithm perspective. And the safety learning, certainly we need to maintain the decisions to be safe during the learning and the decision making process. And the learning efficiency, looking at the learning speed and the conversion performance, there are a lot of work to do from the algorithm part. And the next one, the vulnerability, which is also important part, considering the adverse trial examples in the so-called cyber attack risk. So we have to improve the robustness of the machine learning model, also a very challenging problem. Last but not least, possibility to interface with large language models. So the OpenAI, ChatGPT are becoming more and more popular. How can we make use of them to support our power system operation? It's also a very interesting and promising way to go. Recently, we just published a paper that makes use of ChatGPT to support the power system optimization, especially with the linguistic models. So this is some of our opinions to further make use of AI for the future grid. With that, I conclude my presentation. Look forward to the discussion later on. Thank you.
Thanks for that. Thanks for the talk. We now move on to the next theme, which is on carbon management. And as the first speaker, I would like to invite Professor Viswanathan, who is from the Nanyang Business School, NTU. He's also the Director for Center for Business Sustainability at NTU. This topic will be on leveraging AI for carbon management and decarbonization. Please put your hands together to welcome Prof Vish.
I hope you can hear me at the back. If you can't hear me, I'll use the. If they keep it here.
No, that's fine. You can use it.
Yeah. So, whenever I'm in the energy or sustainability space, especially in terms of research, I put my area and affiliation first. I should mention that. And the other thing I should mention is that most of my teaching is done to executives who are close to CSO level. So, yeah. So most of my teaching is done to executives who are close to CSO level, and my own research is developing algorithms and heuristics for fundamental optimization problems. So these slides were prepared yesterday. I took a step back and looked at leveraging AI for carbon management and decarbonization. So, it can be a bit conceptual and maybe it looks simple as well, but the idea is to take a step back and make it conceptual enough. So first of all, I put both carbon management and decarbonization in the title. And if you ask me, carbon management is a superset of decarbonization. Decarbonization is part of carbon management. But the way the terminology is used in industry practice, carbon management mostly focuses on measurement of carbon emissions, carbon credit generation, nature-based solutions, and so on. So that's why I've sort of distinguished it, whereas decarbonization is eliminating the carbon emissions through the entire life cycle of the product, including in the next cycle, right? So to me, when you look at decarbonization opportunities, it's good to look at the functional focus as well as the industry sectors. And in terms of functional focus, the opportunities in terms of low-hanging fruit, the toughest ones would be energy efficiency improvements, process efficiency improvements, then process design, product design, and finally circular economy, right? And when you look at sectoral focus areas, there are all these hard-to-abate sectors. And to be able to decarbonization opportunities in each industry can be highly contextual and sector specific. Yet there will be commonalities or modular processes. For example, waste cool recovery, waste heat recovery, energy efficiency improvements. They might have a certain context, but to be able to look at some of the industry and sort of make the leap of faith to jump into a different context, that's where probably AI innovations can be applied as well, right? So again, I'm not an AI expert, I'm more of an algorithm expert. What can AI systems do fundamentally? To me, it's prediction, diagnosis, characterization, sensing. They are different words for the same thing. If you're categorizing it, then it's and the technologies used is either lots of data, lots of sensors, machine vision systems, machine learning based forecasting. There is of course generative AI. I struggle with thinking about how generative AI can be used for AI for science, but I'll come to some ideas later on. And then of course decision making, which is optimization, routing, scheduling, matching, and so on, right? So I'm going to talk for just maybe less than 1 minute on carbon management, and I define what is carbon management. It's more about what is looked at in the business world in terms of measurement and reporting, adaptation, nature-based solutions. And you look at any consulting company out there, they claim to have a AI-based tool for measuring Scope 3 emissions. And I was always very skeptical of it. What I found out, so this is, I like Kedar's framework about AI for science and AI, applied AI. So this is where essentially they use text mining. You can have a bunch of invoices of all your suppliers, or you can get the suppliers to tell you where the emissions are from. And I have an expert who's in the audience who's good at applying GHG protocol to report emissions, right? So reporting is of course very important at the corporate world, and there's a lot of opportunities there, maybe in terms of business at least. In terms of research, I think it's more applied research. And essentially these are applications that use ML and text mining to identify categories for reporting. In Scope 3, there are 15 categories under which you have to report it, right? So that's one part. The other part is nature-based carbon credits have taken a huge rap in the recent past. Even though Singapore as a country has been pushing for it in a big way, there's a lot of skepticism about it. And this is where, again, maybe there can be multiple sensors to diagnose and monitor whether the carbon credits that you actually created and sold is actually saving carbon, right? So that's another application. Probably, again, a combination of applied research at the moment, but maybe there is AI for science research there as well. And now I'm going to flash several transparency slides that look at different applications that already exist. There are many papers published. Most of them are probably at the applied level. So you hear about cloud taking up 4% of total emissions in the world because of the amount of energy that is required. So cooling for cloud servers, Google has already developed several AI apps for it. To me, one of the interesting things I read in the newspaper is actually trying to use AI to find out which is the current cleanest grid at that point in time, and to shift cloud operations to that particular point in time because they have backup clouds across the world in a sense. Again, I repeat this point about most applications being very context specific. There's also in the build sector, cooling is another area where these are more process efficiency improvements, energy efficiency improvement as such. Then there is, this is going back to the previous topic of looking at this is more about EV charging infrastructure. I won't go into that, but let me look at managing renewable power systems because I've been doing some research in that area as well. The sense always is that there is a high degree of intermittency in solar energy and wind energy. So Madhavi mentioned about 4.2 gigawatts of energy inputs. We try to create a stochastic program-based models looking at 5 years of irradiance data. And if you're importing exactly 1 gigawatt of power all the time, what we found was that actually you can do back of the envelope calculation. I talked to an industry person in solar. He came up with answers saying, oh, the technology is not a challenge. If you're importing 1 gigawatt all the time, you need 16 gigawatt of energy storage, 7 gigawatt peak. And when we ran the stochastic programming model, we got essentially the same thing. But the thing is, when you have to tactically run the, if you have a world where there's no base load, fossil fuel based power, and you want to minimize the base load backup power, you need to have very good forecasting of the renewable potential for the next day, right? Day ahead forecasting, how do you back up the strategy asset? And that's a huge potential for AI. But to me, the biggest AI for science potential is probably in terms of circular economy, product design, and process design. And let me explain one example of circular economy, a couple of examples. One, I'll talk about tire retreading process. You can actually go to YouTube and look at retreading of tires. And it's a fairly laborious process. The reason that remanufacturing a circular economy is hard to do is because once you disassemble the product, because most of the products currently are manufactured, designed for a linear economy. Once you disassemble the product, you find that there's a huge amount of labor required to actually diagnose the condition of the product, because ultimately you want everything to be recycled, not just back as raw materials, but probably back as components again and again. And if you want to do that, there's a lot of manual process to be done. For example, in the tire case, you need to sort of inspect the tires. There are processes called skiving and so on that has to be done. And these are areas where there's ripe opportunity for actually applying AI to automate the entire remanufacturing process. Today, if you want to retrieve a car tire, the cost of the retreated tire is actually more expensive than a cost of a brand new tire imported from China, right? So circular economy is one area where we can do it. Then the process and product design. How do you actually redesign? This is an article that just came yesterday about AI not meeting its promise because there's a lot of hype there. Maybe the focus is mostly on applied AI research. But to me, really the focus should be on product design for circular economy. Reimagine the entire product design where we are looking at the lithium and the nickel and all the metals being reused again and again so that you don't go back and mine anymore. When you do that, I can't imagine how do you actually redesign, come up with a radical product redesign that is highly modular across time that can actually use AI in a sense. So challenges, most current work are highly domain specific, yet AI-based tools are, industrial tools are very generic at the moment. So need to, those of us who are in sustainability research, we are already multidisciplinary, we sort of understand across disciplines, but now the AI guys also have to come in and understand the context. And only then we can actually make progress in a sense. To me, the other thing is, can we actually develop conceptual frameworks for creating AI tools for energy efficiency, process efficiency, and so on across multiple sectors? Can generative AI be used to suggest low-hanging energy efficiency across, again, different sectors? One example I heard from industry was waste heat recovery in a milk evaporator manufacturing plant. The fundamental physics is you have more surface area, you can recover more heat. And what they did was, instead of having a single pipe, you had large number of pipes. And that's a learning that can be probably used across multiple industries. How do you actually create a database that sort of stores? I mean, there's a semantics and a taxonomy involved in this process in terms of how do you save these ideas in a particular industry, and how can you actually use generative AI to. So when you want to sort of look at an efficiency improvement in a particular sector and somebody else has used it somewhere else, rather than through serendipity or through a consultant knowing this, how can you develop an AI, generative AI engine that can actually take all these ideas in multiple different contexts? So that's actually my last slide, I think. And thank you.
Thanks, Vish, for the talk. We move on to the next talk, which is on carbon management theme, and I would like to invite Dr. Zhiquan Yeo, who's the acting R&D division director, Syntech and ARTC from Kedar. His topic is going to be on life cycle assessment and digitalization for carbon management. Please put your hands together to welcome.
Thanks for the invite for this talk, and I think within this short 10 minutes, I hope that I can throw out more questions than I have answers. So I think this is something that later on we can take the research activities to generate some of the answers that I have. So I'm going to skip through this slide, but essentially what I'm trying to say is, in all the activities that we are talking about in decarbonization and carbon management, all we are actually trying to strive is to either remove carbon emissions from the atmosphere or to reduce emissions into the atmosphere. It sounds simple as it is, but again, it takes a whole lot of collaboration and work to do this, right? So again, there are some of the high-level objectives of carbon services as we speak, and I think in Singapore, what we are trying to strive is also to become a carbon services hub in time to come. And I think there is actually lots of potential for Singapore to have and build this capability to add on to our economy, and because it actually branches into the various sectors, including carbon exchanges, low carbon project development, project financing, consultancy, and monitoring, measurement, reporting, and verification services. So again, this is just a high level overview, which I do not want to belabor too much about it. But what is actually quite useful that to me personally about thinking about what are the challenges of this area is to really understand what is this whole ecosystem, how does this whole ecosystem might look like in terms of carbon services when we talk about this. So of course, first of all, the first stakeholders is really the carbon credit buyers, which essentially points to the companies who have sort of already typically pledged their net zero target by say 2030, right, or 2050. So these are the one big stakeholder in the market, and they are the ones generating the demand for carbon credit because of their pledges. But of course, to support these stakeholders, okay, there are challenges because like what Prof Vish has mentioned. I think even computing their scope 1, scope 2, and even scope 3 emissions can be a challenge. And I think currently what Singapore is trying to do is to establish a national carbon emissions registry to help companies in sort of performing scope 3 emissions currently. But of course, this is just an initial stepping stone for future AI research to come, because what I see in this area is that scope 3 emissions is actually a huge scope, in the sense that there are actually 15 categories. And even let's say just zooming into one category of say purchase goods and services, it already extends into infinite possibilities of what kind of data sets that needs to be created, and are we able to create those data sets more efficiently moving forward. On the other hand, these are the supply of carbon credits where these are greenhouse gas project developers. Of course, then they will be actually looking for say technologies and promising technologies that can really remove or reduce carbon emissions in the physical world. Of course, then there will be investors to fund these projects. But then again, common questions by developers is, even before putting in the money, am I able to get a promise from these technology developers or project developers to say that how much carbon emissions is being reduced or removed, and what's the potential of these technologies before I put in any money. I think even in the research landscape, whenever there's sustainability related or kind of research proposals, one of these common questions that is being asked by the review panels is, how much reduction are you promising before I put in any investment into funding your research? So again, is there any tool to help them, help us even project what kind of potential reductions or sustainability improvements at a very, very early stage to support these investment decisions? So that could potentially open up an area for AI research as well, because we could potentially learn from past data. So again, of course, once you have a project, then you have these third-party auditors, and this is where very manual processes are being done to say do sampling, do checks on to ensure that some of the data that's being reported are true, and how are they able to ensure that the things that they are reporting are actually reflective of what is really happening on the ground, right? And then of course, once these third-party auditors go through this process, then they will have to go to a carbon offset program where they will actually pay some fees in order to maintain a registry on what are the carbon projects are available in the market and how they are. And this is where carbon credits are actually being generated for the first time. And of course, once this carbon offset program generate the carbon credits, they will be thrown into carbon exchanges and the marketplace, and this is where price determination will occur. And then this is where market clearance will take place. And of course, this is where the carbon credit buyers will be connected to the project developers through these carbon credits. So again, this is a whole sort of a snapshot of what this whole ecosystem looks like. And of course, from there, this understanding, we could actually sort of tease out some research challenges and some problem statements relating AI that can support this whole ecosystem. So this is how the connection is made, and these are some of the exemplary the goals that I represented company. Right. So another thing that actually has just come out earlier this year is that in the European region, which took effect just recently, a few months ago, that any companies moving forward having a green claims need to comply, the requirements is that they need to actually show substantial evidence of sustainability benefits moving forward, and hence we actually anticipate more demand for life cycle assessment studies in the next 2 to 3 years. But of course, for those out there who have been doing life cycle assessment, to understand that doing such studies is a very manual process, very data intensive process, and typically the bottleneck for such a study is usually the data collection portion. So how are we able to utilize AI to actually fill up some data gaps or even generate certain simulation model automatically to actually fill up some of the data gaps to actually boost up the productivity of this very, very manual process of life cycle assessment. Right. So again, how I see these current services ecosystem, it has to be supported by two main pillars. One is really about the greenhouse gas project innovation, where this is a lot of physical and natural sciences capabilities will take place. Things like renewable energy, clean energy, energy efficient projects that was mentioned. Carbon capture, sequestration, and land use and afforestation projects will take place. And of course, it has to be matched together with the greenhouse gas accounting and quantification pillar, which actually represents a little bit more of the computational and data side of things to sort of maintain this sort of high-level mass balance of whether these carbon, where are these carbon actually generated and where are they being removed or used. So again, having limited time, I'm just going to quickly go through this because I think these are actually quite familiar and it was also presented previously by Prof Vish. So again, in the whole landscape of things, there are actually many methodologies out there, right, governing the quantification, governing verification, validation, and it actually operates at different levels of analysis. It could be in terms of corporate level, emissions, in terms of project, and in terms of product kind of accounting standards. And in particular, for product accounting standards, there is actually this thing called life cycle assessment to help to measure carbon emissions relating to producing a product over its entire life cycle. And of course, there is always this sort of interlinkages between organizational reporting as well as product level reporting. But of course, currently they are actually seen very separate exercises. So I think moving forward, there could be even further streamlining of process to ensure that there's a reconciliation between the different standards out there. So again, in terms of going back to even the act of generating carbon credits to begin with, all these sort of carbon offset program have specific methodologies for specific activities or specific technologies relating to removing or reducing carbon emissions. Again, if you were to look at the whole list of methodologies, you will realize that it's in fact very activity specific. For instance, let's say there's improved forest management in temperate and rural forests. And this is a particular activity that needs to be established and is associated methodology needs to be established. So again, are we able to streamline this methodology creation as well as implementation? Because this is actually a very time-consuming process and it's actually could be a bottleneck, right, to the supply of carbon credits to the market. So again, this is again the last slide where I just provide a very high-level snapshot of some of the challenges as well as the opportunities that I see in terms of this whole area of carbon management and decarbonization. So again, first of all, in terms of the carbon methodology development, like what I said just now in terms of technology, it's very case specific in terms of its nature now. Are we able to learn from adjacent cases and then from there quickly create new methodologies for any new technologies that will emerge? In terms of time, effort, and expertise, how do we actually streamline it? Are we able to utilize AI to really learn from these adjacent cases? And in terms of emerging technology projections, again, this is where investors are very interested to understand, are we able to discern promising versus non-promising decarbonization technologies at a very early stage or as early as possible so that we are able to minimize the amount of money spent in investments that really lead to a dead end. Of course, with such a technology, then we also have to be very mindful about minimizing the false positives and even false negative rates, because that will potentially mean that you're getting off projects that may not make sense, or rather, killing off projects that actually make sense, but actually showing sort of this false negative results. Right? And of course, in terms of sensing and monitoring, are we able to design methods for more cost-effective and fit-for-purpose methods to even measure and monitor this? Because in terms of data acquisition, there is actually sort of different ways of deriving this carbon emissions number. Right? One is direct emissions measurement, where you are actually putting sensors directly to measure the inflow and outflow of these gases. But of course, there are other methods, for instance, could be activity or proxy-based methods to compute these carbon emissions. Of course, there's always this balance between cost and accuracy versus the ground truth. And are we able to find that balance in terms of are we able to derive these carbon emissions in a cost-effective manner, but as well as without compromising the accuracy? So of course, relating to that, this is where, are we able to learn correlations between the activities and its associated emissions using large data sets? So one example, it could be even estimating emissions of, say, vehicles, for instance. Are we able to say, there are different ways of measuring this particular activity, right? For instance, you can actually put sensors in the tailpipe, or alternatively, you can base off the amount of fuel that's being burned, or it could be in terms of distance-based kind of measurements. So are we able to, learn certain correlations so that we need not, rely on direct measurements, because that could be a costly approach to acquire such data set. Right. So in terms of after measuring, then you actually look at the data chain of custody, where there's of course opportunities for digitalized validation and verification process, and as well as integrate data from different chains. So in this case, there could be different, say, blockchains that can carry a lot of all these data sets together. But in future, are we able to ensure that data coming from different chains are able to interact with each other and be coherent with each other? As well as, last but not least, are we able to ensure the data integrity of all these data as it's processed from one party to the other? And finally, in terms of quantification, monitoring, verification, and reporting, firstly, are we able to utilize AI to fill up some of these data sets, data gaps, using large existing data sets? So again, this is where coming to the point of let's say performing a carbon emission modeling and carbon emission life cycle assessment is a very manual process. It involves a lot of manual data collection. So again, the team performing such a study might need to go down to actual sites, collect actual production figures, so emission figures. So are we able to fill up some of these data gaps through using existing large data sets to sort of make certain level guesses, and then from there further refine all these data inputs? Are we able to also think about non or less intrusive approach to do quantification, monitoring, verification, and reporting as well? Because again, if the direction is to sensorize everything and to rely on all these direct measurements, it's going to be a very costly affair to collect all these data. So are we able to design or even come up with non and less intrusive approach to do so, to do this quantification and monitoring process? And of course, in terms of life cycle assessment and carbon accounting, are we able to even automate this whole process of doing such studies? Because again, it's a very manual process today, and it actually requires a lot of manpower and effort to even establish such a study. Of course, one approach is to hire more people. The other approach is really to streamline the process of creating such studies. Right. So again, this is just a short snapshot of some of these challenges and opportunities that I see that's being associated with this whole area of carbon management and decarbonization. And of course, it's more, I'm looking forward to have a further discussion on what are the other areas that can be further explored relating to this. So of course, this is the last slide. Currently, what personally I'm working on is on this life cycle assessment platform that supports the efficient computation of carbon emissions and other environmental impact indicators across the supply chain. And currently, we are also working on a Singapore emissions factor registry that tries to gather as much data as possible to help companies to report especially their corporate emissions, focusing on the scope 3 emissions, which is actually the most challenging part of it. Of course, this is again just a first step into helping the industry in such a challenge. Of course, moving forward, we are also welcoming more ideas on how are we able to apply AI to help us to accelerate this whole journey. Yeah. So with that, I'm going to end this presentation.
Thanks for that. Now we move on to the next theme, which is on electrification. And in this, we have two talks. The first talk is by Dr Anshuman Tripathi. He's the Senior Program Director in Ariane. His topic is going to be on AI for electrification. Please put your hands together to welcome Dr Anshuman.
My research in Energy Research Institute is on future mobility systems and advanced power electronics. So there are two important words here, future and advanced. Right. So that's also the biggest challenge in creating applied research in these two areas, future mobility systems and advanced power electronics. So over the past 12 years, my group and I have experienced a few things, and some of them are summarized in the first two slides before I move to electrification. So if you see the left-hand picture, these are the components that go and make a internal combustion engine car. And on the right-hand side, we have a drivetrain of an electric car. So while on the left-hand side picture, it was manual efficient and it was powered by manual efforts. On the right hand side, we have a software that can really drive this particular drivetrain or powertrain. This moving towards mechanical systems designed for manual operation to a software driven system, which is an electric car. So things are moving from mechanical to software systems. This is one of our experiences. Another example you can see by the line that I've drawn in the bottom. If you take a smartphone, most of the activities that we used to do physically can be done by applications which are also examples of software approach. The other important thing that we have learned over the past few years, especially with our work on autonomous vehicles, is that instead of simple coding, which is if then else statements in computer programs writing software, we are slowly moving towards learning approach or evolutionary approach, and that is essentially the backbone of any AI-based system. So this is something that we have experienced over the past 12 years of our research in developing autonomous vehicles and also developing power electronic systems that interface with distribution power networks. One of the examples that we worked on was solid state transformer. Again, it was conceptualized by Dr. Yeo, who is also mentoring us in these efforts. So with that, the idea here is if you are not moving towards, if you are not evolving towards systems which are AI driven, soon we will be in the back seat of the technology evolution. So how do we do that in electrification? And these are some of the points. We have not done much on this yet, but these are some of the points which have been which comes to our mind. So how do we define AI in terms of electrification? So electrification itself is something which replaces mechanical systems or software-driven systems with electricity-based systems. So that is electrification. Secondly, why do we do that? What is the objective? So the objective is clearly to optimize and enhance electrification efforts through artificial intelligence. So that's the objective. And this is something which is the backbone of my presentation. Why do we do this? In Energy Research Institute, we only deal with industries. And industries come up with a lot of this data that is supplied to us from two major industries that we work with. One of them is the utility, and secondly, the electric vehicle industry. So if I could replace many of these softwares with learning algorithms, I have a potential in each of these areas: reliability, production, safety, energy consumption, and emissions, to save multi-million dollars for these industries, or two industries only. The first industry is utility. The second industry is vehicles or electric vehicle industry. So this is the data that we got in 2022, that enables, or that shows the promise of AI for these two industries only. So that is why we have to do AI, and that is the business case that should drive all the AI research that we are supposed to do. So I have chosen 3 areas for my talk here, and these 3 areas are related to the work that we do in our institute: energy management, mobility, and renewable integration. So renewable integration is a broad topic. Prof Nuruddin covered quite a bit of it. So I'm going to quickly go through our experience in these areas and the requirements thereon. So first topic is on energy management, and we have three areas here. Smart grid systems, we all know what are smart grids. Predictive maintenance is something that helps us in predicting the maintenance requirements of a given power plant, for example, or a fleet of electric vehicles, for instance. Then energy storage. How do we bring in energy storage? Energy storage itself is very expensive, whether it is connected to a grid or whether it is carried on by electric vehicles. But then, is it possible to optimize that? You see, so these are the 3 areas where AI can help us, in managing more optimally the energy management systems of it. In terms of mobility, we had a lot of experience in terms of getting EVs onto the roads in a most energy efficient way. And we have used AI systems to help us. We managed to put sensors in 26 electric vehicles of the same type, cars, for example, and we got some data which were promising enough to improve the energy efficiency of these electric vehicles. The second important part is the charging infrastructure. So if we have to electrify all the fleet in Singapore by 2040, charging infrastructure is going to be very, very, very important. How do we fast charge? Where do we put fast chargers? Can we get rid of petrol pumps, for example? Can we have electric charging pumps? So how do we spread it out? So this is also to be done by artificial. We have some experience in doing this. We created an electromobility roadmap for Singapore. And in this roadmap, we also laid down what should be the process of forming charging infrastructure for a city-state like ours. Then, more importantly, battery management systems. So this is more specific to both the electric mobility, but also it is equally important for grid-connected energy storage. Yeah. Finally, we have renewable energy integration. Prof Nuruddin covered quite a bit of it, and some of it relates to the forecasting. But more importantly, the 2 last bullet, demand response management and microgrid management, is something that AI can really help us on. So I have listed down 3 important challenges, and you can say future directions as well, opportunities as well. And this is out of our experience also dealing with autonomous vehicles, which are like sensors as well. So if you have a 12-meter bus moving around in a neighborhood with 200 sensors, the neighborhood might get skeptical of what data these guys are taking. So my colleague Niels here is helping us with data privacy and security, for example. Then integration with existing systems, it will not be possible for us to replace all what exists today. It will be too expensive. It is not cost effective. So how can new systems with AI equipped can integrate with the existing systems that we have? And finally, I think this has been covered by the previous speakers as well. What should be the regulatory and ethical considerations of collecting data, using it for your advantage in a given segment? So these are the three important steps that we would have to consider when we write down the script for next generation, which is AI-based technology. That was my last slide. Thank you so much. I'll be happy to discuss further.
Thanks, Anshuman, for that. So we move on to the next talk for the electrification theme. I would like to invite Dr. Ren Yi, who is the head of Energy Materials Department, IMRE, ASTAR. He will talk about components enabling electrification and incorporating AI. Please put your hands together to welcome Ren Yi.
Good morning, everyone. I'm Ren from ASTAR IMRE. I'm leading a department called Energy Materials Department, and this department primarily deals with any research work that links to batteries. And you can see the topics. I think battery is definitely a key component that enabling the electrification. And we will see how AI actually supports these component developments. Okay, so when we talk about electrifications, we always think about the fast-growing electric vehicles, EVs, and then the large electric power in the provided by the EV batteries does not just power the electric motor. It actually powers multiple sensor and communication systems. And together with the ultra low latencies offered by the electric propulsion system, which enables better control and maneuver of the car, this actually enables what we call AV, the autonomous vehicles. And that's why we see autonomous vehicles, EV, always linked with electrifications. So if we think EV as a product, as a component that enable electrification, actually this answers our topics already. But in today's presentation, I want to deep dive into this. If we think EV as a product, then how AI can help to develop its component, EV's component. So that's why, and this further extends to how we use EV or how we use its component. So as I mentioned, battery is a very key component within EV, within AV. So if you talk about batteries, AI has already been applied in how we develop, how we research on batteries. For example, from the perspective of battery material discovery, from the perspective of formulating the adaptive formation cycles, and also from how we design the battery, how we design the battery pack. And then, of course, linking to how we recycle battery, how we manage their end of life. And then we think the EV as a product, how AI has been helping in developing this product, involving how we design the EV, how we design the motor, how we actually make sure that the manufacturing is out of defects. We see a lot of many AI applications in how to analyze the defect image coming out from the manufacturing process, and then how we do virtual testings of those EVs. And then we move on to the use phase. We may actually use the product. We may actually use the component. For example, if we talk about batteries again, the AI has already been applied in the battery management system mentioned by some of the earlier speakers as well. What we do with AI in the BMS is actually enable friendly health diagnostic predictions, better control, optimized control of how we manage individual battery cells. And then if we talk about EV as a product, then how AI helps, of course, mentioned earlier, is how they enable the autonomous driving. And then, of course, as mentioned by Prof Tripathi also, that AI has been playing a lot of roles in how we charge EV. how we deploy the chargers effectively, efficiently, how we use AI to enable adaptive and smart charging. We also link to how we match the demand and supply, which enable dynamic pricing. So all is actually already been, there are some potential that AI can play. And then if we think about even higher level applications where when the company manage an EV fleet, this is where we can talk about route planning, when and where the car should be charged or even maintained. But the key thing is, when we talk about electrification, it's not just about mobility. And actually, when I dig out the definition for electrification, it can be mentioned, it refers to any technology that replacing the energy-intensive processes, which requires fossil fuel. So a lot of this topic actually is under electrification, and it's already explained by the other presenters in the earlier presentation. So I won't cover that. But in the next couple of minutes, I'm going to showcase what is actually happening in the research community, how AI has been applied in battery research. So the first topic I'm going to showcase is really this battery material discovery, or we call accelerated battery material discovery, that's happening in A-Star in IMRI. This project is really led by, I believe, Prof Madhavi, and the IMRI's team here is trying to build a high throughput battery electrolyte discovery system. And for this work, actually, it branched out from Kedar's work as well, because Kedar is working on this platform that can accelerate material discovery. So what we do here, or the question we try to answer is, given a set of precursors, how we can actually identify the best material, including how they should be processed, what is the formulation of the material. So our team actually built this modular system. This modular system can actually formulate the material, process the material, and then test the material by itself. And the good thing is it provides the data sets. The inputs is actually the formulation, the recipes, the processing conditions. And then the outcome is those characterization results that link to the battery performance. And then all this data feed into the machine learning model. And the machine learning model can actually suggest the next test it should be running. So this form of closed loop system let the machine itself try to navigate among the matrix of all the parameters, so they can quickly define the best material from this system. And interestingly, even you zoom into this small module about formulations, it actually itself has a dedicated or separate trained machine learning model that enables the machine to handle liquids of unknown viscosities, because this is actually very challenging when you do automations. So they actually have trained a model here to handle that in high accuracy. The next topic is moving from the battery materials. We talk about battery health. All the batteries the capacity start to fade upon cycling. But the degradation mechanism is very complex, involve many parameters, causes, and often that is actually not linear. So this actually sets the potential of how AI can actually help. So this team work on 60 plus commercial LFP battery cells. They try to cycle aging those cells, and then they try to correlate the discharge characteristics with the residual capacities. And then they use all this data to build a model. That model can actually precisely predict the remaining useful life of the battery. I think the accuracy is up to 95%. And then in a separate attempt, when they try to correlate the reconditioning conditions of cells with the residual capacities and build up a model that can actually predict how much capacity you can recover by doing the reconditioning process. So this is how we actually apply machine learning in battery analytics. And then the last topic I want to cover is this fundamental science in battery modeling and digital twin. As mentioned by Prof Nodding also, that if you talk about modeling, based on physics, based on knowledge, there is, but they don't really require data. That's a good thing, but it's actually slow and sometimes inaccurate. But if we move on a pure data-driven machine learning, and then it actually demands a lot of data, and it demands the quality of the data. So what this team trying to do is trying to marry the physical world and the cyber world. They try to inbuild the physics and knowledge of battery degradation mechanism into the machine learning. And the challenge is how to represent this model, the degradation mechanism into the machine learning algorithms. So this is where the team is coming in and trying to figure out. And then by doing that, in the end, it really enable we to build digital twins, which can actually visualize, explain, and interpret the battery performance. And further down is how we can use the digital twin to predict or test the battery health in the long run. So this is actually what this team is working on. That's actually the end of my presentation. I'm actually aware there are a lot of ongoing projects that have the element of AI. And I know there are many proposals in the pipeline that also incorporate AI. I really hope to see all these proposals landed in the research community. Thank you.
Very much, Weng. So we move on to the last topic for the day, after which we'll take a short break. So this topic is on urban nexus. We have two speakers. I would like to welcome the first speaker, Professor Man Pun, from the School of Mechanical and Aerospace Engineering, NTU. He'll be talking about urban nexus of systems and potentials for AI. Please welcome Man Pun. Put your hands together to welcome you.
Morning, everyone. I'm given the challenge of talking about the AI and urban mixes in 10 minutes, which I think most of you know that is impossible. And it makes even more impossible if this attempt is done by a garage mechanic. So I'm going to do two things to save myself. Number one is that my talk will not go into the details of the AIs, but instead I try to facilitate the later discussions on the possibility. Another attempt I'm going to make is I'm going to zoom down to a particular area within the large space of urban nexus. And I try to do that by making use of the particular situation of Singapore, why I want to zoom down to one particular area. First is we are having one of the highest population density, and this density I'm talking about per unit land area. So therefore, it leads to the second point we are talking about. We are a city-state, meaning that we are a country of the size of a city, right? So we have small land area, and 100% of our population is urbanized. So definitely, this is something very important to us. Perhaps we are the only developed economy in the tropical belt. So I try to highlight the keywords here that give me the envelope for me to zoom down to one particular area. Whatever we want to do here in Singapore, because of our smallness and because of our density, perhaps anything that takes a lot of land area to do is not a good idea. And I'm talking about perhaps some of the renewable energy. Why we use fossil fuels before? Because fossil fuels have very high energy density. Right? Renewable energy, some of them, right? Solar, wind, they are not particularly high in terms of energy density. So if we were to pursue this kind of renewable energy, right? So we face our constraint. Hydro is very high density, energy density, but we don't have any hydro. And our economy is highly developed. So if we were to deploy certain urban solutions, that is at the expense of our productivity. Right? One very common example is, we still hear it today, okay, if we want to save energy, let's raise the aircon temperature by a certain degrees. Right? We can do it right now. Right? But why don't we do that? Because that is done at the expense of our productivity, which I suppose our productivity is way much higher than 26 cents per kilowatt hour. Right? So we rather spend that 26 cents for our productivity. Okay. So therefore, I want to make use of the Singapore case to zoom down to one particular system in the urban nexus, which is building, right? Outside of the many related areas or systems, food, water, materials. Okay. In Singapore, I would argue that this one is important. I hope this one does not offend humanity. It's the buildings that matter. Okay, so let me bring back what is actually supposed to encompass in the urban nexus core, just to prove to you that, okay, I'm not leading you to distract from the topic. Right? So this is a report, I get it from UN, which is about the urban nexus. They define certain systems is actually at the core of the urban nexus, in which, of course, the sustainable cities, in this case, I will take it as buildings, and also the energy systems are at the very core. So therefore, I want to zoom down to this particular nexus for these 10 minutes. Okay, and I'm fortunate enough that some of the earlier speakers has already done all the heavy lifting about the buildings and also the power grid. Okay. So let me very quickly go through my point. Right. So in Singapore, again, because we are highly dense and our economy is highly developed. Okay. At present, we spend about 41% of our electricity on industry, about 5% on transportation, but this is the biggest one. And this is the one that surely we want efficiency. We want to use less energy to run our buildings. But again, as I mentioned, we do not want to sacrifice our productivity or our well-being in doing that. That's where the smart buildings, intelligent energy management come into the picture. We want to manage our building using AI, for example, right? To do it smartly. Can we save energy without sacrificing productivity and well-being? And if we look up one more scale, okay, so let's say we are able to do this for our building, right? But we are also having some sort of zero carbon target we have to meet, right? So unavoidably, we have to bring in more and more renewables into our cities' power system, right? And well, renewables are good, right? But they have problems, right? More renewables means more intermittency, more volatility into our power grid, right? And I think Professor Lavin earlier already mentioned, grid resilience is number one. It is unquestionable. It must be achieved, which is basically in contradictory to what we are trying to do. Right? Unquestionably, it has to be resilient, but at the same time, we try to bring in as much volatility as possible. So therefore, we develop solutions, right, to counter that, right? And of course, we need to link up those solutions to the problems that we are trying to solve. So the power grid and smart control comes into the picture, right? So that we can deliver our power to our industries and buildings without interruption. Right? And hopefully along the way is free. Now here comes the question, if we were to be green and we were to be smart, right? Do we still have something can be done at the building level? Right. These are some of the examples. And can we still do something? If we were able to do the building, can we do it in a way that the buildings can also benefit the grid? Right. So that's why we come to this kind of solution. Right? Building themselves as thermal battery. Right? So, and in my opinion, is so far we are heavily underutilizing this. Right? When we try to do that, we always try to, okay, let's put a PCM energy storage there. Let's put a storage tank, ice storage tank. Because by doing that, you feel that you are doing something. Right? But the buildings in Singapore, we have roughly 150,000 buildings. They are sitting there already. Right? Why don't we make use of them before we start to install something new? Right? That takes, of course, some advanced development of control. Right? And in my opinion, this is currently lacking. Right? This one, perhaps you don't need me to explain anymore. I think there are works doing on this already. So therefore, it comes to the recently rather buzzword. So we try to allow flexibility in our buildings. Right? Be it using its own thermal mass or be it using some additional systems. And once we are able to do the buildings, how about we do a cluster of buildings? We aggregate, right? So that the impacts can go all the way back to the grid, right? So we go to a demand response, and perhaps the most recent, the most fuzzy of all the fuzzy words is the building to grid integration. And I believe there are a lot of opportunities for AI in each of the purple areas. Make the efficient, make the carbon intensive low carbon, make the reactive become predictive, make the standalone systems to be connected. Right? So we have a coordination between energy systems and hopefully we achieve what we wanted to achieve. This is probably the biggest problem I face. Because I coming from the building area, so I've been working on smart control systems for buildings. Okay. Predictive control, and buildings can also be a small system of systems by itself by integrating the renewable and also the energy storage. The grid community has been doing a lot, right, on the renewable integrations, optimization, smart grid management. But what I can see, what is currently lacking is really the interface between the two. This is the part that is lacking. We look around the world, we are not alone. We are not the only one who is lacking the interface between the buildings and grid. Perhaps this is so far one of the most successful demonstrators. I can see is the Northaven district. So I think they have 9 buildings, and then they also have a district heating and cooling, and also shared energy system, trying to demonstrate that buildings can play a role in the grid. We are also not lazy in Union. We try to go towards that direction. So we have the renewable energy demonstrator, which is largely focused on the grid. And we also have attempts made to the building. So this is the work that is done by my group. I try to use the building thermal mass to play a role in controlling the building. So this is one of the results. So if you go back to your office, try to set the 24 degrees C as your set point. And I believe you will end up spending very little time and 24 degrees. Most of the time, you will be either hotter than 24 or cooler than 20. Right. It is because of the control we are using in buildings are not that smart. Right. And hardly they make use of the building thermal mass to stabilize. So this is a demonstration. If we are able to put in the thermal mass into the control, and if we were able to put in a predictive algorithm, we can control the temperature very safely. And along the way, we found that we can save a great deal of energy, right? Just by avoiding overcooling conditions. Again, this is my garage mechanic had come to mind again. Is that whatever I develop on the lab, I need it to work in reality. So these are the examples we have done so far in Singapore. And surprisingly, so far, we save never less than 20% by this all the buildings that we have tried. The highest one we can even save 60%. Right. And bear in mind that that saving is not by sacrificing the comfort of the people. We even stabilize the temperature your experience along. So that is my proposal to the Greek people. Hey, we are here. We can play a role. Don't leave us out of the picture. Okay. And the world seems to be going into this direction. So in fact, I just came back from Prague on this IEA effort. You can see they are first by having an annex for making the buildings flexible. The one that I just closed last week is the Annex 81. What we try to do is to make building digitalized. And these are the oncoming works, is to how to make use of the digitalized building to become energy flexible and becomes integrated with the city's energy system. And there will be a new annex coming up. It's so new that the number is not even assigned. That is particularly on the grid integrated control of building. Okay, perhaps this is the last slide. I want to leave it to the audience here to invite discussions. This is what I imagine our future power system, that building can play a role in it. Thank you, Ray.
Thanks, Manpun. We'll definitely not leave the buildings alone. The fact that you're giving a talk says that that's a very important part. So we come to the last talk for this morning session. To give this talk on urban access, I would like to invite Mr. Praveen Chandrashekar, who's from Savannah, Jurong. He's the Director, NEP and Environmental Design for Building Subsidies. He will talk about transformation, complexity in an urban ecosystem. So ladies and gentlemen, put your hands together to welcome Mr. Praveen Chandrashekar.
Thanks, Madhavi. Good morning, everyone. So it's always been a pleasure to be a last speaker because I'm expected to be finished 10 minutes ago. So I know I already covered in 5 minutes, but I understand that's my role today. It's not to deep dive, but to consolidate some of the strategies that each one of you subject matter experts have shared into a solution that solves some of the pressing issues that we have in the built environment. So I'm from the company called Savannah Jurong. We are one of the largest urban infrastructure and managed services company based in Singapore, but we have offices in 40 countries. So that's that introduction. Maybe I'll keep going. So I've been asked to just keep it very short to see some of the just touch base on what are some of the forward topics that we have and where AI can play a role. And also these topics are very much aligned with Singapore's research, innovation, and enterprise framework that we have. So I've categorized this into 4 pillars. One is the advanced construction, so it is robotics and automation, design for deconstruction, innovative construction process and resource efficiency. So we have some speakers who spoke on this recently and before me, and then on the resilient infra and smart system, going from predictive preventive to predictive maintenance. I know yes, AG has done a lot of work on this. They have been doing on this. When although I'm not a researcher, we did involved in certain research project with NTU for SJNTU Corporate Lab, and I've been involved in GB grant project with DCA. So we've been working on some of these initiatives. Next is durable and maintainable buildings. That's where I feel a lot of AI should come in. DCA is struggling to push design for maintainability. There's a lot of pushback from the industry. Technology, the barrier is all laborious to check design for maintainability, although we have been drawing, even we are not able to sort of class detection at this point. Next is advanced and smart building facilities. So as everybody knows, Singapore Green Plan has a very ambitious target to green 80% of the building, and also 80% of the new building should be solar energy, and the best in class building should achieve 80% energy savings from 2005 levels. And it's not a single bullet that will solve all these problems. I think maybe a combination of solutions that I think the experts spoke today have to come together to achieve this green plan. And also there is next pillar on sustainable built environment. So where we're talking about climate ready built environment, I think one of the speakers, I think Prof Yeo mentioned that every year we're getting a new novel on what's happening with the climate. So recently, I think in March, Dr Zhiquan Yeo 37 degrees close to the right side. So it's every year we have a new benchmark, which we thought is happening only 50 years down the line. So our air conditioning system has to work harder, it has to be more efficient to make sure that we keep up with the climate. Other important topic is advanced cooling technology. So this something is, I think there is another agency that is looking forward to getting touch base on this much, but that's where I think much of the effort will go in to reduce our reliance on air conditioning, how to see passive ways of cooling, means more cooling, scenario-based cooling, powered by AI, innovative sustainability features, and the last one is livable and healthy cities. So we cannot discount this. Everything we're doing is for people to make sure that it's livable and that people are happy, people-centric and help our design, nature-based solution for climate change and data-driven urban planning. That's something that affects our business as well. When we do the new master planning, the key thing is the data and how we use the data for an effective urban planning. So this is what we see from a built environment. Today, I'm actually wearing a cap of from a built environment, from a consulting angle, and also representing some of my clients. And this is what we see as a holistic sustainability approach for some of our project developments. So this is what I would say some of the research has been happening, and later we can discuss some of the topics that were discussed this morning. And some of these trends, I think I say where I can see AI is coming, but not fully there. And this definitely affects the way we design, construct, and operate the building. For example, AI for construction management. I can see that some new technologies. We also met a few from MIT recently who are actually doing AI for construction management and how we can use technology to make it more productive, more faster. Regenerative AI for design optimization. Definitely, I don't want to take the job from the designers, but that's what is happening. So, but nobody is losing the job. It's just that we are upscaling ourselves to the new way of designing systems. So that's, I would say, it's very important. We are investing ourselves in this plan. AI in building operations. This is a very, very big topic. In order to achieve the long-term goal of decarbonization, we need to make that our existing building stock is efficient. 80% of the buildings in Singapore are existing buildings. Without greening them, we cannot hit our green target. So I think Prof Man Pun mentioned on this. I think that's its core capabilities as well. So that's where we also doing some research on this. We are implementing AI-based plant optimization for nexus. And lastly, AI-based material transport for building construction and deconstruction. I think Prof Vish Viswanathan also mentioned, and a few other speakers mentioned on carbon management. So it's very important. And some of the bottlenecks when we talk to our consultants or even our counterpart consultants, also our other stakeholders, which is importantly our clients. Some of the key pushbacks that we get is lack of codes and standards for the use of AI. So it's very in a very I would say infant stage. I think it has to be incorporated in some of the standards that is easy for I would say designers like us to implement. High capex outlay, I think everything is we talk to a developer, everything only the dollars and cents move it or a regulatory approach. So cost is I think something that we cannot ignore. Lack of off-the-shelf product which can be easily plug and play. Also, we have so many AI it's still not
very much for the I would like to put your hands together and all the speakers and what's going to happen is where we want you all to put your facilities together to have the feedback discussion. So maybe while we are switching this, you guys can go take a quick bio break outside. There's also food, coffee. You can bring it back inside during the discussion. Yeah. So we'll see you at about 11:05. Thank you. So colleagues, please bring your food and come back in. We'll start with the section from each table. So for the first one, I would like to call who would sort of condense what their table was focusing on future.
Okay.
It's going to be a bit chaotic.
Yeah, I know that it's very hard to get your attention while you are eating. So this is an additional challenge to me. And actually, by the way, I require your attention. In the back, and you come back here. Okay? Please, I require your attention.
On the back bench.
And I should tell you one thing. I should have your attention at least. Because I'm a little punisher, they didn't want to give me food until I make a presentation. So I'm making a presentation while I'm hungry. So, listen, please listen. Okay, here what we come up with the group. It was very intense. It was very, very intense. And one thing that I would like to start with is once we finish it with all these items, we made sure that everyone agrees on those items, which means that this is an agreement. We reached an agreement, although the discussion was extremely intense. So we followed actually the recommendations, and we started to highlight only specific issues where really there is an added value of the AI. It's not because AI is fashion or we can expect some AI opportunities, but we identified actually key issues where AI has an added value. An added value ensures that if we don't have models and we need AI models to complete those models, or because we don't know actually the behavior of that or that, and then we need AI in order to improve that behavior, or because it's too costly today and we need AI in order to improve the performance and the cost, etc. So all what we have identified so far are really the items where there is a need for AI as an added value because there is a limitation of the knowledge that we have today. So the first one I told you already, this is not a surprise to you, because I told you that the first issue that we are facing is the grid resiliency. The grid resiliency, of course, is multi-issue, because we have, of course, the energy balancing, the network management with the regulatory landscape, policy consideration, cybersecurity, climate, etc. It's a multi-factor. And why this is important? So the first thing here, I start with the issue here, and then jump immediately to the challenges and the bottlenecks linked to this item. The item, why AI is needed, because the complexity is growing. The complexity is ever growing, which means that the complexity, I told you, the complexity is first the vulnerability, which means the vulnerability is increasing and we cannot afford having the vulnerability. The second thing is also because of the cost. If we don't master everything, complexity, then the cost is increasing in order to face all that challenges. We have also the fact that we have interdependency between the infrastructure. The core grid is not standalone structure. It is connected to digital network. It is connected to the water. It is connected to the telecommunication, and it's interactive. We have situation of the resiliency where we had an issue, for example, in the communication system, and we had the failure propagating, and we don't understand actually the interdependencies, and we need to understand that, and that's why AI can have an added value in this issue. Of course, as I told you, the climate change. Climate change is new for our asset, and how this climate change is impacting the reliability of the asset, but also for the predictability in the future. So that things it's a new for us, it's open, and we need to understand a variety of aspects for the resiliency itself, and also the effectiveness of the data and time span, because we have data today, but we don't know they are relevant in the next future, and its relevance for the resiliency as well. This we need AI tools, because physical or just deterministic models, they are not enough, and they cannot be used as data. Forecasting, we have all, I think, the ministry, they have talked about the forecasting and prediction. And this is in many areas. Of course, one of the issues that was linked with the electrification is the EV charging, but also EV contributing to the system in terms of services, what we call G2D, and the link with the energy system, predicting the behavior, predicting the fleet, predicting the charge, predicting the state. All these are open ideas, and then we need there the help of the AI, because we have a geographical and time different scale. We have all the different, for example, in forecasting, it's the different if you have in one area to the other, but also forecasting at the short term, it's much more difficult, for example, than with modern, and forecasting on local area is much more difficult than forecasting at the larger area, the geographic and local area. We have models, for example, with 3% model of custom consumption behavior. If it's at a country scale, because of compensation of error, we can get 3-5% error. But if we go to a local area, then we don't have compensating factors, and then the error is 30, 40%, 50% error. We cannot afford that. Then we need, of course, the AI in that perspective. The other issue is the flexibility. The flexibility is a key point in smart grid, for example, because we have uncertainties, we have variabilities. We don't have controllable devices. For example, if we have the intermittency of renewable energies, that we don't have controllable generation to keep the balance. Where we can get that balancing? Of course, the only way is the flexibility. Flexibility is in multi-issues flexibility, because we can get from storage, we can get from demand, and I would like to make the link to my colleague this morning saying, hey, from the building, don't forget us. No, we don't forget you, from the building. So the building is important, because there, in order to get a complete use of the flexibility of the building, we need also to understand the behavior of the occupancy, the competitiveness of the EV action on the energy, the comfort, because we can, the flexibility, we need to forecast that if we don't take into account the human behavior, that we cannot have that correct forecasting of the flexibility. In addition, it is highly distributed, and we need to move from a responsive to a predict what would be, of course, the flexibility. As I told you, one of the challenges, human in the loop and visibility of what's going to be there, and the provision. For example, in the power grid, we predict what's going to be tomorrow at 9 o'clock, and we have to be extremely precise. That if we have a generation that is controllable, that's okay. But if we rely on flexibility that we are not sure that it can be there, then it's a big problem of provision and visibility. Then the asset management. I talked about also that in asset management, predictive maintenance. The infrastructure, one first issue I told you is the resilience. The second big issue is the infrastructure. I told you that we are facing the second revolution of electrification. In 25 years, we need to move from 20% of electricity use to 60% electricity use. We have never in humanity experienced such a movement. And this brings the challenge of the infrastructure. And the infrastructure, we need to master everything in infrastructure. It's development, investment, and particularly its maintenance. And we need to move to this predictive maintenance. But predictive maintenance, actually, the problem is that we have the problem is that we have a variety of assets. The quality of data is not completely mastered. The compatibility of the models between the assets, etc. And most of the others is that for the predictive maintenance, for example, most of the time we use past data, historical data, whereas we are converting to future evolution. So this adaptability of the past data to the evolution of the infrastructure, the match is not there yet. So we need also that AI to the techniques of AI, the foreseeable kind of business that we use in order to face this asset management on the future development. The last one that we talked about is the overall energy cost reduction. I told you also that when the complexity is growing, necessarily the cost is growing in order to ensure that we use AI in order to enhance actually the efficiency of the economic value, the economic impact, of course, but also grid interactive with the smart grid because the landscape of the energy is changing and the value. One of the examples that we have with in Europe, I will share it with you. We have a large development of energy communities. The energy communities with what we call self-consumption. The problem is that the self-consumption, they are subsidized and they consume their electricity that they produce locally, and they use the grid only as a backup. However, the model, the economic model of the grid is that everyone is using it because there is a difference in use and there is an economic value of the usage of that grid. It's totally changing. It's totally is upheaval today because some of the people that are using the grid only for backup, whereas actually they need to contribute to the whole economic model of that grid. So this is an open, fully open, and in that perspective, of course, in terms of the economic model, we have the complexity of obviously the intermittency, rest import when is there is really rising, particularly from Singapore, of importing some of the energy based on this renewable but variable intermittent energy. And in that time, well, what will be the real-time monitoring control when we have this variability and we don't know exactly what's going on in the external grid that we don't master. So that we need also AI model for observing, and then from that observing, we issue real-time models and monitoring as well. Because how to observe when we don't have enough data external grid as well, and pricing mechanism as well. So that pricing mechanism. So these are the four that we trade five items, 5 challenges, and then when we come to the AI needs, from our understanding. The issue in AI, we're not like to talk about what are the AI techniques suitable for that, it's not that issue. But the issue is that it's the AI evolution. Are we assured that the models of AI that we are using today will be valuable in 10 years? We don't know that. So that the AI evolution over time is important. And what we need is we couple actually this interactive AI with human expertise in order to couple with this evolution, because that's the only way. We are using in the power industry that our assets, physical assets, they are planned to spend at least for 30, 40 years. I told you that in Europe we have assets of 60, 70 years. 20% of our assets are 60 years old. So now we have a fast evolving technique, and we cannot remove that all the time. So we need also to couple with human expertise. There is one term which is sustainable AI, because we have today in parity, just AI, you have to know that the consumption of AI is fast growing. We are facing on even securing those servers of 600, 1,000 megawatt. Never seen that in the world. Never seen it. And finally, as I told you, ask any operator, any utility operator today, could you let the AI techniques take control of all your grid? You will never find a single operator saying, yeah, I trust the AI to take over the control of my grid. You will not find it. But the problem is, we have to give to AI some of the, particularly this distributed level, some of that control, not totally, but some of that control. So one issue in terms of AI need is really the trustable AI. Trustable AI, which means that we need to work on that at least this is the expression that need is the explainability and verification that what is provided is really what is needed in resilient time. This is we cannot afford saying that okay, if it fails, then we can put just control and delay and then we start again. You can do that. You cannot do that in future, particularly with 60% of the that's not possible. Okay. Adaptability, combination of AI technology, because we have different AI, and I have indicated earlier that finally we find out that there is no AI1 technique that fits. Usually because of the characteristic of all those problems, we need the combination of the AI techniques. It needs combination. And particularly, then I'm putting forward what we have, not me myself only, but many speakers this morning saying that clearly we need to couple the AI technologies with the physical models. The physical models, because AI techniques by themselves, they are not sufficient. And the physical model, because they add the knowledge to that model, but it comes also with some limitation of the AI. That's also what is important. So we need to have edge devices, more measurement devices, more information sourcing in order to make sure that, of course, we still supply our model with adaptable information. And finally, some of the colleagues here, they pointed out the fact that there is an impact of geopolitical conflict and data privacy, interconnection with device system, for example, saying that well, we have in Thai people, you can jump in whatever you want. Okay? In Thai people, they don't necessarily understand the same thing of AI. They don't understand. They don't use the same data. They don't have the same regulation. Whereas we need to be interconnected, and we need finally when the electrons they recirculate, they don't care that these people they speak a different language or they have a different culture or whatever. The electrons they don't have borders. And that's one issue of finding one area that is adaptable for the different culture and so on, etc. And particularly when we have this interconnection between the system, there are multi-layers, multi-voltage, multi-regulation, multi-actually control mechanism. And then this is also where AI can facilitate. It can be one layer that facilitates this kind of. Okay, I hope that was not very too long. I tried to summarize my colleagues because all of them they agree. Okay, all of them they agree. If you want to add something, it's up to you. If you think that they haven't covered all what you told me.
Thanks, Prof Ren, but we need you here.
Okay.
We want to open up for any questions or comments. You know, we didn't have much time in the morning, but any questions, comments on what Prof Ren has presented, please, there's a mic right on your table. You can just use that mic to ask a question.
I would love to hear from you. I have feedback from you because you know how we said, when we don't have questions, either you have understood everything and agree with everything, or you don't get it. So you choose.
Yeah, so this is also open to online. We have some participants. If you have any questions, you can just key in the chat box. Any comments or questions? Maybe I get the ball rolling. Oh, Vish, you have, okay.
Yeah,
Vish, there's a mic right there so that online people can hear you.
Mine's more of a comment. So the second part about the challenges and bottleneck, and this is what Singapore is doing right now. When they're importing the 4.2 megawatt, we are actually going to build dedicated pipelines to. So to me, I think the future is where you will rely on the regional grid or the global grid when you have a breakdown event, and that's the time when you want it. Otherwise, you want to be sort of firewalled and disconnected as well. Otherwise, the problem becomes too complex to sort of manage. That's what I'm sort of understanding over a period of time. So maybe even before we use AI, the paradigm in terms of how the grid of grids or global grid is going to happen, there has to be some kind of an agreement. Because otherwise, if you keep everything open, that's going to be disaster. Right? So, and in a sense, I mean, that's the Singaporean policymakers going to just rely on undersea cables at the moment rather than trying to talk to all the ASEAN neighbors to build a grid at the moment.
Well, first of all, I agree with you. Yeah, I agree with you. And you mentioned some of the key words. You mentioned the key words. Words is complexity. It's complex. Keyword is global issue. Keywords, we need to have a kind of agreement. All these are the keywords. Just let me jump in to provide the experience that we have in Europe. In Europe, we have many countries. We have many countries, and they exchange their interconnected. Of course, one important is to have a coordinated exchange with coordinated rules, and everything is coordinated. But although it's coordinated, we had almost in 2006, because there is a ship crossing in Amber, and there was a mistake from the grid operator. We were close to having total blackout, a whole girl. Because of one event, one small event, which is normally easy to handle, that things are getting complex. And now we are getting alarms and alarms. Why is that? Because of the renewables. Because the renewables, they are not controllable. And that's the issue. They're not controllable. We are seeing flows that we don't know where they come from. Someone told me, those uncontrolled flows, it's someone that comes, hits your car and disappears. That's what uncontrollable is. And you're right, that to do that, we need to observe that we don't have necessarily the thing. But even when you observe and you see some issues going outside in, I don't know, Thailand, Laos, whatever, that as a single player, how you can get the control over the. But if you say that, oh, if you have a contingency, then I can just be standalone, then that means that you will oversize your system again. You have the cost issue as well. So the number of issues of that complexity, they say, and that's why also those open issues, we still have to work on physical models, but also on the data to help to overcome some of the issues that today there are.
Thanks, Prof Naradi, for that, and thanks to your team. We'll move on to the next table. You can enjoy your lunch now. Yeah, thank you for that. So the next one, we have mixed it up a bit. So we will go to carbon management. Vish, you can put your feet on because that's online.
Okay. Okay, maybe I'll try this mic now. So I'm going to very quickly summarize the discussion we had on the table, and then maybe Zhiquan can add on to whatever I say. So my goal when I started the discussion was go away from the data and start discussing product design, process design, circular economy for actually doing decarbonization, but very quickly realized that when you want to focus on decarbonization, there has to be a focus on the sector. And we couldn't sort of agree on a common sector. So the entire discussion was actually on data management itself. So if I were to suggest a potential grand project title out of this, I would say liberating AI for data integration and synchronization across multiple levels with a sectoral focus or something like this. So for instance, at the company level, they do GHG reporting based on global greenhouse gas protocol. To me, as a decarbonization researcher, that data is completely useful because it's at such a high level, scope 1, scope 2, and scope 3. We cannot really look at that for a company to actually decarbonize. That's my. So you need to have data at a product, process, and a project level. So in a sense, the people in the sustainability office have to prepare that, and then of course they have to prepare this to be actually able to do it. And that's a complete waste of time and effort in a sense. So is there a way to actually do bottom-up integration of the data? Can we actually connect the LCA data to the GHG protocol data? So that's the data synchronization part. There were other examples similarly, looking at companies reporting scope 1, scope 2, and scope 3. If all the companies are reporting, why do you need to actually have the scope 3 data collected by one company? There should be a way to actually have a blockchain-based effort that can integrate the data collection. And our colleague from nature-based solution was talking about how in the nature-based solution area itself, there is different levels of data, and the different levels of data don't necessarily always synchronize in a sense. So the idea was, how do we actually integrate the data management to be able to eventually do decarbonization? And Yeoh also came up with the idea of right now when we do NDCs, nationally determined contribution, we only do scope 1. But more and more there's a rallying cry to actually look at scope 2 and scope 3 for a country level as well. And when we do that, again, how do you integrate from the company level to the country level? Because whenever people report sustainability results, everybody is cynical about the data. So that's a challenge when it comes to data. So a combination of LCA along with different other sources. So we need to get, so if you are looking at data and if you sort of put up a proposal which says, we are going to solve all the data problems in the world, nothing is going to happen. Because as scientists and researchers, our interest is really not to collect data because we want to use the data to do things. But unfortunately, this is the dirty work that has to be done by somebody, and it requires actually a multiple groups with multiple interests to come together, have lots of conversations to even figure out. I mean, the computer scientists use the words like ontology and semantics and so on. So we need to even have a conversation to even figure out what is the kind of data that we have. How do we actually conceptualize the data into frameworks that can eventually help in terms of creating a synchronized platform. And of course, the AI people have to be involved in the conversation right in the beginning, because if they're not involved in it at the beginning, it's going to be just a tape solution of some standard algorithms. That doesn't help. So that was a major part of the discussion. So when it comes to challenges and bottlenecks, there was a long list. But what it essentially says is that we have these multiple sources of data, and none of us really understand the data. So again, how do we synchronize the data? How do we understand the domain level information? So of course, if you are doing a large project, 5-year project, you have to start small and decide that we're going to maybe focus on particular sectors, get the learning there before we go on to other sectors, because that's how you can really make a change. I do believe this is somewhere fitting somewhere between applied AI research and AI for science, because this is something everybody talks about and says we want to do this, but nobody is keen on doing it because that's not really their core methodological or research interest in a sense. But given that we are all interdisciplinarians, this is something that needs to be done, especially at a national level, so that there is actually more informed decarbonization effort in respective sectors. Right? So that's sort of a summary of everything that is captured. So AI needs would be to eventually be able to integrate the data, look at there are some micro level projects that can be done as well. So there was a comment about grid emission factors, not just grid emission factors, emission factors in nature-based solutions, emission factors in the grid. Right now, nobody even knows how we are collecting it. You are obviously not measuring the carbon directly. Most of the time, it's either based on input activities or output activities, and then we are using some standard formulas. Why are we using a standard formula? Shouldn't, as scientists, we actually verify it? Even for a simple thing like a SBS double-decker bus or a SQ flight from point A to point B. Are the emission factors actually telling us what it is? So that is a relatively low-hanging fruit. If we actually cooperate with a particular companies or sectors, we can put in some sensors and we can put in some science models and maybe some AI models there as well to verify it, so that those are things that needs to be done at a granular level as well. Anything else to add, on top of it? Anything I missed out?
So I think we just by large.
So I think just to add on, thanks for the summary. I think it covers most of the points. So again, I think leading on to the next step after carbon management or carbon services is really about decarbonization. And I think to get that right, the actions that we are able to create with decarbonization really depends on how granular or how well informed are we in this performing this initial step of measurement and management. Because if we are actually relying a lot on high level information, highly aggregated data, then the type of mitigation actions that we can derive is still fairly high level. So if we want to go down to very technology specific or sort of issue specific decarbonization strategy, then this is where we really have to ensure that we are able to create those very granular information to really determine what are the root causes, what are the parameters that are within our control that we can actually affect. Yeah, so I think that is something that moving forward, what do you think about?
So one last thing to add on the decarbonization part. Some of the other sectors have been discussed. Don't ignore buildings, don't ignore energy generation. So there are other sectors like chemical and so on. So even while the data management part is going on, there probably has to be looking at product design, process design, circular economy, using AI in each of these sectors as well. Because that's where the real meat is. The data part is not where the meat is. But if you don't do the data right, then the rest of the things will collapse.
Thanks. Thanks. Thanks, Vish and Vishwan, and all the participants on the table. Any questions or comments for Vish or for the table rather, on the carbon management? I totally agree that it's a very sector specific and we need data not specifically from each institution, but like a rather sectorial. Any other questions or comments for the table?
So I come back to the question Prof Madhavi had, how do we close the loop? So can you throw some numbers? What is the percentage role of data in closing the loop versus the physical side of things? Which comes first, or what's the way forward?
In terms of impact you're asking.
Yeah.
So let me answer. I'm not sure you can give a percentage, but these days, every grant call, including grant calls by ASTA, they ask us to justify based on data, right? So if you don't have data, all the claims are after there. And we find that even great companies sometimes get found out because their claims are wrong. So, I don't think you can put a percentage, but given the fact that there's so much of billions of dollars being spent on research, this is actually a very low-hanging fruit in a sense. It's a very painful research, but it has to be something that has to be done, and it cannot be done by one person or one silo. That people have to get together and have lots of conversations before you can even figure out what exactly needs to be done. So I sort of chickened out and didn't give you an answer.
No, that was close enough. It's difficult to quantify, but which one you have?
Yeah, exactly. It's still fairly difficult to quantify.
I thought you were going to give a percentage.
Yeah, I also don't want to give a specific percentage, but I think, more and more, I think whenever we make decisions to say invest in certain technologies, decarbonizing, we are always faced with the challenge of how do we even know what particular technology has that kind of amount of promises that it tries to claim. And I think one approach, of course, apart from AI, we're also questioning ourselves, are we able to utilize more fundamental science to even inform certain technologies? How do we derive sustainability advantages for certain particular ideas that we generate out? Are we able to even have that sort of chain of causality of how a particular technology can lead to decrease amounts of carbon emissions, for instance? That kind of fundamental process has to be in place first, and then after that we come in to sort of have some estimation in that kind of carbon reductions that are more or less reasonable. But I think that is one of the approaches.
Thank you for that. With that, we move on to the next table, which is on electrification. Who's going to talk on?
Yeah. So I'll try to summarize what we've discussed. And as I listen to the points being put forward from the previous breakout session, seems like there's a lot of overlap. There seems to be many common points and sort of validating in a way that we're along the same line of thinking. So we had members in the group from different industries and backgrounds, so we had different perspectives and also found some common ground. We started our discussion acknowledging that there are a lot of opportunities in terms of cost savings. If we focus on implementing AI in improving the reliability, safety, and also reducing the energy consumption and emissions. This will be for both utility as well as the mobility sectors in terms of electrification. We had a point on optimizing processes in the industry so that in turn again brings us cost savings. So this can be very specific to chemical industries, for example, or can be across other industries as well. When it comes to electrification of maritime as well as aviation sectors, you can use AI to optimize the charging infrastructure usage, depending on the usage and optimize the
the assets as well. And this is one of the points that was put forward as well. And when we talk about electrifying, there's a huge transformation of replacing the non-renewable energy sources. And in these electrification efforts, and AI can be used as a guiding process or as a guide for this process to implement all of these transformational changes. And when it comes to EV sectors, so we can use AI for increasing the safety and reliability, especially when it comes to automation or battery fire safety, for example. This is where predictive analytics can come in to avoid any failures in not just operating these assets, but also in the manufacturing processes. So that's a great boost in terms of safety. That's where AI can help. When it comes to energy storage systems, not just in mobility applications, but also static applications, grid applications, and where we have distributed energy storage systems across, and if we have to combine them and manage them in a large scale together, and that's where AI can help in optimizing the usage of these distributed energy sources that are spread across. Another point adding to it is in terms of planning. And again, I think this is something that was put forward in the form of forecasting the demand and optimizing the usage and real-time planning of these assets like EV fleets, for example. When it comes to various challenges and bottlenecks, I think some of these points were overlapping with the previous breakout sessions where we have issues with data privacy and data collecting quality data that can improve the accuracy of these AI models. So that's a huge challenge in validating and making sure the data is actually useful for the right use case and making it perfect fit for the application. And another challenge could be integrating these new systems with what is existing legacy systems and not causing much of disruptions and making sure that both the new systems and existing systems work together seamlessly. There can be ethical and regulatory constraints as well, which needs to be addressed. And one of the other challenges is the reasoning or the trust behind how AI comes up with a certain decision, and how do we make sure that we validate it and trust, and basically a point that was put forward where we hand over the entire grid operation to an AI system, which is we're not very confident in doing so. So how do we ensure that we can validate, and how can humans be involved in making sure this can be reliable and basically make it more useful and trustworthy. Another point that we discussed is the computational speed. There can be decision making by humans where it is in real time and quick decision making where AI can help. But at the same time, we have to make sure that these systems are fast enough with lower latencies and at the same time accurate enough to replace human decision making where quick decisions are needed in any industry process. Another challenge is standardization of the shared data, which was also, I believe, discussed in the previous session. And the difficulty of having non-harmonized data and making sure how these can be shared across different applications. And there's another challenge that we discussed, which is the complexity of the number of different AI models and understanding what model is a perfect fit for a particular application and deciding the best use case and adapting them to the right use case would be a challenge. And in terms of considerations, we come up with a few points on basically getting awareness so that we can have the right AI implementations that can help address these challenges. Again, quality of data is another challenge, like we mentioned. So filtering these data and providing robust data that can improve the accuracy of AI models, and more importantly, human behavior data that can take these AI decisions closer to human-like decision making. And one of the points that was also discussed is while we use AI systems to optimize energy production, distribution usage, and optimize the whole energy grid infrastructure. And as we address or as we make these decarbonization footprints and mobility roadmaps a reality, we'll have to also consider that the AI systems that are forming a huge influx of DC loads are itself a huge load on the grid, and they have to be sustainably powered as well. So that's a quick summary of the points that we discussed.
Next slide. Any questions?
Yeah, you went to the last one on the energy use of AI. Have you had any discussion or thought of when to use AI and when traditional technologies might be more efficient? If you look at the use of AI, I was last year at the conference on AI and efficiency, and somebody gave a scary presentation that the computational power in data center is doubling every 2 months. 2 months. It's doubling globally due to new AI applications, and that another forecast I've seen is ChatGPT is going to use the same amount of power as the rest of the world is using today by 2035 if it increases by this. So, but we also had some very nice examples that if we use AI and we try to make it perfect, we also going to burn up the planet. AI is going to destroy the planet not by robots and everything else, but just because we're using so much energy for the AI. Have you been taught about how to optimize the use of AI and how you make it different that AI makes sense and AI is just a very fancy way of doing things which could be done more efficiently in another way?
I think we touched upon that point, but I believe we have to use AI tools to ask them how to optimize their AI. Yeah, but if my numbers are correct, I think right now the data centers are using about 7% of the grid store, and it is growing at a faster rate. So I think that's one of the key considerations that we have to take into all the roadmaps and footprints that we are moving forward.
Just a quick question to the group. I noticed that based on your presentation, for example, if you look at point 3 in your first section of electrification, seems to be focused very much on direct electrification, whereas in the sectors, especially the transport sectors, for example, there's obviously a lot of interest in power to fuels, for example, which is, you can say it's an indirect electrification. They are using electricity to produce e-fuels, for example. Was that something that was also discussed on whether AI can help in those very difficult areas?
Yeah, I think that's a good point. We touched upon briefly on that aspect as well. I think that's a good point that we can do here.
Any further questions or comments before we move on to the last group? Okay, thanks, Bob. So we move on to the last group session, which is urban nexus. I think we'll be sharing.
Yes, our people is potentially important effort. We have diverse group. Sorry. Yeah. Our table discussed the urban nexus and the opportunity for AI there. There's quite a diverse group of people on the table, a group of engineers and architects. And if you need to know something about engineers and architects, is that we can never agree on anything, right? But somehow today we agreed on a few things. And so we'd like to, in the next few minutes, to share on these things that we definitely agree on amicably. Right. So primarily where we see the use of AI is that it should be used as a
decision making, right? And the AI is used to make those decision making more productive, more efficient. And the decision that we want to make, right, is about how to make the urban environment more sustainable. So, in summary, AI is used for decision making around sustainability. So, what underpins that is that the stakeholders in that urban environment assess the value of being sustainable, which is debatable, right? And that will be a recurring theme. We go through these points. Yeah. So, right. So, which part of the urban sector should we use AI, right? And we've identified a few use cases for AI. Urban farming came out a lot. So too about monitoring and improving the well-being of citizens. We also talked a bit about using AI to characterize certain elements of heritage. And we also talked about using AI to help architects to make decisions on selecting the most sustainable material. And finally, and this was something that Man Pun talked about in his presentation earlier, in the operations and maintenance of the building, a decision needs to be made every few minutes, right? And so that's something where you should definitely outsource to AI for it to be optimized. Right, so come to the challenge, which is very interesting. One of the things that comes up very often, like every few minutes in the discussion, is that there is a lack of a common data sharing platform. We've done a lot of research, in fact, publicly funded research, but this data seems to be hidden behind some kind of wall, and whether the agencies or the respective PI somehow have certain reluctance to share data. Data is what the researchers need to push out these kinds of solutions, and they advocated for some kind of research foundation, perhaps of the national variety, to manage this data and yeah, and perhaps make it available for people to leverage on it. Yeah, digitalization of the built environment is a great enabler. We see that if you do take the effort to digitize your building stock, to digitize the amount of materials that you use, and also to categorize what kind of materials are out there in the built environment and how much they affect your decarbonization efforts, that would be also very helpful with their decision making. So they point to countries like Hong Kong and Denmark, where there have been efforts to maintain a repository of your building stock and what materials have been used. The table also advocated for establishing some kind of urban observatory where we can monitor and track these things. They did mention that this is something that could be driven by the private sector because there are some commercial benefits to having this kind of repository. But what is needed before the private sector can take this on is that there needs to be a push, right, from your lead agency to generate a demand for this, because this is something where in our discussion we've arrived at the conclusion where the market will not drive itself, right? So you do need you do need to design your policy around the need for these kinds of sustainability solutions. Yeah. And finally, we also talked about the human element, and that's something where ultimately that's what the buildings are for, right? The buildings are for people. And so do we really understand the type of people that are in our building? Not really. There are many of these archetypes that we're not quite sure how they would respond to certain changes. We completely about how elderly might respond pretty differently from young people. And so again, to quantify this is what we need to do. Right. So that brings us to the last one. About the AI needs, and this a lot of it centers around manpower. So AI expensive in our case because there's not enough people. But even as we push, right? Let's say we roll out certain manpower policies and training to increase the number of AI professionals in the urban space. The concern is that certain skills
will be problem, right? As people become a bit too reliant on AI, will they lose certain contextual the ability to contextualize the thing that they're designing for? That is the concept. And so this is something where you're in training your AI professionals for this stage, you also need to provide them with this the ability to contextualize. Again, it centers around designing for people, right? Yeah. So again, once again, you mentioned data platform. Please, if anyone who is listening who can create the data platform, please, right? And also, I think the other enabler that we talked about is about setting certain standards. Again, standards will drive demand for these solutions, and so yeah. So there needs to be certain standards on how AI is used and what materials we should use in our building, and what let's say minimum energy use for the building, or sorry, maximum energy use for the building. So again, we point to the example of what Man Pun raised earlier about setting your temperature, right? Whether people can accept that they can 6 degrees set point. But if that's your standard, then people will it, right? So yeah, that's all.
Any question? I will get you about asking question.
Yeah.
I help you.
Okay. I'm not scared of him, so I'm gonna ask a question. One thing I'm missing here, and I'm not sure, one of the things I think we can make big benefits is by integrating different parts of the urban nexus, grid and everything. So one of the areas, one of the things is a hot topic in Singapore at the moment is urban heating. And there's been maps opening in big places in Singapore, the hottest that with Marine Parade and Bahan, it's in the list of the hottest places, the region all the time. One of the area is also sustainable design, because if you use more energy and then you have more urban heating, you have more air conditioning, we have traditional air conditioners, if you have traditional air conditioning, they heat up the environment effectively more. And that way, in theory, one thing is if it integrates sectors, districts, estates, have district cooling on a large scale, and then the district cooling, as shown by Man Pun this morning, is effectively a big energy store, because it's involved with energy store, which you can use if there's a grid fault and if the required demand is strong, you can effectively instantly switch off the cooling and still maintain the temperature for an hour due to the heat, the storage event. All this stuff to me relies on AI to analyze and predict. I think it's too complex to model. Have you looked at that kind of applications? Scaling it up and also looking at the interfaces with other areas, because urban nexus, you interface with actually everything. You interface with the grid, interface with electrification, the carbon accounting comes in. Have you looked at also at you're the nexus? So have you looked at the interfaces with the other areas?
And Praveen can add on details to this, but what we did that this is something where you get the push down, right? Top-down push from maybe your lead agencies or big demand drivers, the developers, then there's something that can be done. But without having first this someone generating lead demand for this kind of entry level organization, is unlikely that the market will arrive at this point. Right? Did I summarize it well? Yeah. Great.
Yeah, but then I think, do you need AI to show to those lead drivers that this makes sense to do on a big scale?
Can we show this?
Let me add on. So I think I do agree that it should be a holistic approach, because we have various market abilities. But we need to discuss how to connect together everything into one single umbrella, and how it makes sense to deliver the national goals. So that has to be a top-down approach policy. And then how this will be enacted into each of these areas. So that's where the private sector will come in and run the show. But we need the agencies to take the policies, provide the incentives,
deploy the platform for the systems to get connected together and give that kind of policy. Does that drive, you mentioned here repository material buildings. Yeah. Does it drive the need for a general concept of, I don't know, I almost will start to think that if you do an NRF funded research program, one of the requirements is that the data becomes available in central repository. It's already there, it's now distributed. You and US or whoever, and finally we start making the data available. Would it make sense that certain data might be stored in a central NRF program, is not controlled, and other agency controlled repository that you really create LTA for your own data model, but I'm thinking about having the data model of data warehouse or so you can have the data. The problem is how to make the sense of it. That's very important. What matters to a layman, for example, what matters to parents, if you want to select the material which is resident for the next 50 years, how to select those materials, whether it makes sense. So you need to make sure that the data is preserved and convert it into very layman terms that the stakeholders can easily pick it. If it is a very, I would say, at the highest technical level, they may not be able to understand it. So that's why we start that from the availability, quality of data, how to interpret it.
Yeah, next question. We need to end up here. And one of the things that we did discuss a lot about how exactly want to define this and quite often when we design this buildings, a lot of the benefits are positive externalities that don't translate to commercial gains for the person who's actually spending the money, right? So that if we have a set point for shopping centers, it's not that big capital land can then charge their tenants more from having this higher set point. There's no value to them directly. So these benefits are what we need to occupy to make the case that you're talking. Okay. Okay. Thank you. Thank you. Neil, when I was in NRF, I used to ask you all these questions. Now it's up to you. Okay, but I must say that urban nexus is really a large-scale complex system. So you did mention it's a close loop. One thing affects the other. So you really need to solve it. You really using complex analysis. So that's where AI comes in. And AI will be able to help you to solve this kind of issue. And I also believe that modeling and simulation, I mean, before you cut metal, if you can you incorporate AI into modeling and simulation, then you can uncover a lot of non-obvious kind of outcome. Actually, 2014, I actually issued a challenge that if you can reduce the urban heat island, we can reduce the urban temperature by 4 degrees real fun, and there were no takers. But now you look at, I mean, there was some study by Grid, they say that if you look at the temperature in downtown versus Lim Chu Kang, the difference in midnight is of 7 degrees. So to reduce by 4 degrees, I think we can do it. So I give this challenge to you, and if you have a solution, we will find. Okay, so but for today, this is a very important workshop because Madhavi and I, we're going to write the white paper, and if there's lots of opportunity, we will have funding from NRF. So this is something that we hope to get this moving, and AI for sustainability is really an important area. I would have to rephrase the title to, it should be saying, Sustainable AI for Sustainability. That should be the thing. Okay. So I must say that today, this is an excellent collaboration. I see lots of refreshing ideas in very enthusiastic speakers. I think this is really very comforting to see this. So I would also say that, I mean, what we are looking for is excellent science that's taken. The other aspect is impactful. So we talk about what percentage to constitute, whether it's to accept AI or not. I would see that there are two aspects. Impactful in a sense that if I can save energy by 30%, 40%, I say it's impactful. But if I can save energy by 1%, in fact, we're talking to one wafer fab, and then they're telling us that they can save energy 1%. That 1% translates to $30 million a year. Is that impactful? I think it's impactful. So percentage and absolute value will be important. I mean, if you have to justify a proposal, these are some of the numbers we are looking for. And you talk about computational power, you talk about AI, ChatGPT doubling every month. I think this is I see that's what we call an unintended consequences of that. And therefore, I've been talking about what are the challenges. Energy consumption is always an issue for AI, so we want to use it judiciously. Digitalization, just for info, it contributes 1.9 gigaton globally, compared to aviation 0.9 gigaton. So digitalization is also an energy guzzler. So although it's an enabler, it is also an energy guzzler. So we want to make sure that we use AI, we use it judiciously. Smart grid, I think excellent presentation. Smart grid covers almost every aspect of smart grid that we are looking at in Singapore. So AI is one of the key. In fact, I went to visit ABB lab, and then you were telling me that they use AI for a manual fault detection, detection and identification and isolation from a 60-minute fault, they reduce it to 15 seconds. This is a kind of impact that we're looking at. And decarbonization, if we talk about grid resilience, I think grid resilience is important, especially if we talk about how we can manage contact with high uncertainty. That's where AI will come in. And AI will normally try to dispel a confirmation bias by using hypothesis. So I think some of those is useful. Carbon management, I think this is really a key area that we really need to focus on, because there's always issue of validation and verification, and this is important to prevent greenwashing. There's also talk about modeling and simulation. I think if you can get AI to predict an impending cloud cover, for example, then you can actually power in less expensive backup power to actually buffer the sudden loss of intermittency caused by solar energy. Instead of using battery for 1 megawatt of solar, you use 1 megawatt of battery to buffer. I think this really is a waste of money. So that is something that I thought is useful, that you can leverage AI. And circular material process design, I think those are the useful areas that you can optimize. Optimization in those really you can use AI to optimize to a large extent. I was just told that Alibaba, they came up with a term called green AI, which means that what they do is that they can they pull all the data, and then they get the AI to actually write report for them. So those are some of the things that you can really see potential application for AI. Context-based AI being looking at granular data, I think those are some of the important aspects. And I know that ESA group did quite a lot of M&S to uncover non-obvious outcomes. So there was a case whereby Malaysia banned chicken coming to Singapore. Right? So we bought from Brazil. So we always ask, wow, all the way from Brazil, the carbon footprint must be very high. But it turns out it's the other way around. The carbon footprint buying frozen chicken from Brazil is actually lower than from Malaysia, because actually the processing, you consume 40%, and they have a lot of hydro power, green energy. Transport only constitutes 4% of the carbon footprint. So this is not obvious outcome that I always say that if you do modeling and simulation, you use AI, you can uncover this. But we're talking about frozen chicken. But you want fresh chicken, don't buy from Malaysia. Okay, then AI in electrification, I thought this is really important, especially we talk about EV charging. EV charging with limited power capacity, for example. Now we look at all the HEV as said, they don't have enough power. So how can I do this? So AI sometimes is able to actually manage power charging to, let's say, a few or several EV by managing the how much power flow to each vehicle. So this is important. And somebody mentioned about EV on reliability and safety. I think this is also key. If you look at how SCDF take care of EV fire, it's really a very difficult job to do EV fire. So they actually have to use cover to actually cover the just to make sure that they prevent oxygen from going in to sustain the fire. So if you have solution from AI, I think it's something that SCDF will be very interested to look at. And then nexus, of course, I think also talk about overcooling. I think this is important. Therefore, you talk about AI for control. AI for control, I think this is one of the most useful part of control, especially for the building management system. But there is what I call perceived productivity. Actually, there was a study that you are actually better off, you're more productive at 35 degrees compared to 22 degrees. But if you do a survey, the starting point from a lot of the researchers is, no, I'm better at 22 degrees. But the cognitive performance studies show otherwise. Because the body temperature, you function the best at 36.9. So if you go at 22 degrees, a lot of your energy has to be expended to actually warm up your body, leaving less energy going to your brain, which means you are less productive. So at 35 degrees, there was a study by NUS says that actually you are more productive 35. So it's a perception that you always think you are better 22. So I want to dispel this perception. And you see, if I can set my aircon from 22 degrees to 25, I save 34% of my energy. And this is significant. So I think this is important that some of the perception we want to make sure that through social behavior study, you will be able to uncover. There was a study last time when Create was doing they started with a vehicle, the EV, right? And then they want to minimize the number of amount of aircon because they want to save power. So what they do is that they just blow aircon on your face. So this is what I call perceived cooling. You cool your face, you actually whole body you feel that you are cool. So there are some of this behavior part. I think you really need to make sure that we take care of this issue. That means not only technology. I'm sure technology will solve our problem, but there's always this human behavior part. And I always say that you can have the best technology for sustainability, but people don't know. People open the window when aircon is on, and they don't shut the fume hood for their lab and so on. So I think the ultimate contributor is still you as a human being that we able to do that. And even like what you eat is important. So today when I came, I look at lunch, I make sure that there's no beef. Beef constitutes 18 grams, that's for a portion of 300 grams of beef. 18 kg of CO2. That's how much. Chicken is 1.8 kg. So we have chicken. Not that we are sustainable. But I would want to say that if you have a glass of wine, 0.3 kg of CO2. So that's the lowest. Let's drink wine. Thank you very much.
Yeah, I think, thanks, Vivian. I think with this, we close this workshop. We thank you all for attending and taking active participation. And I think all your comments and feedback have been summarized, and we will keep you informed of the next step. Thank you very much and have a great day.